Welcome. So, as you may or may not know, so one of the highlights of the Information Theory Summer School is that we have a special endowed lecture, the Padovani Lecture, that's awarded once per year, and it's selected jointly by the organizers of the IT school, so that includes myself and all of the members of the program committee that you see in your program, and as well as the Board of Governors of the IT Society. So for this year, we're very lucky and honored to have Professor Kannan Ramchandran as our Padovani Lecturer. So he is a professor at the University of California, Berkeley, where he's been since '99. Prior to that, he was at the University of Illinois. He's won a number of awards, most recently the Kobayashi Award in Computers and Communication, recognizing his work on codes for distributed storage and compression. And he's also won a number of paper awards. So for journal papers, I think 2 from the Signal Processing Society, 1 jointly from the Information Theory Society and Communications Society, and another one from the Communications Society Data Storage Award. He's won a teaching award, a big teaching award at Berkeley from the East Department in 2009, along with many other accolades. So we're very honored to have Kannan here. For me, it's quite special because Kannan was one of my first professors when I was a grad student, like you guys. So from 2003 to 2009, so he was one of the people at Berkeley when I was there. So it's really very happy to have you here.
Thank you very much, Bobak. You're reminding me how old I am from the time I remember when you were a grad student. I also wanted to make sure that we recognize Bobak for running this IT school almost single-handedly. So let's give him a round of applause. Okay, so I don't know if I can live up to the billing, and especially to follow after Tara, but we'll see what we can do. And also, you guys have just had lunch, so it's a good time to snooze. I won't mind. Go ahead. I would have done it if I were you. So the title of my talk is on duality, encryption, sampling, and learning. What's all these words, right? The power of codes. Well, this is a information theory school, so we always start with paying tribute to Shannon, right? So Shannon has incredible legacy of communication, channel capacity, source coding, channel coding, cryptography, sampling theory. And he made very sizable contributions, breakthrough contributions in all these areas. But and many more. If you didn't know, he was also, his MS thesis is the Boolean logic for switching circuits. The field of digital logic took off from his master's thesis. He was also an avid juggler. He had juggling theorems where he characterized the time the ball spends in the air to the time in the hand, and he worked out all these equations. He was also, he tinkered with lots of things. He was a unicyclist. I mean, the list goes on, okay? He was a crazy dude, okay? Brilliant, but crazy. Okay, so here's the story, in case you haven't seen this. If you have, apologies, but this is as narrated by Arthur Lubel. I think he's at BU, if I'm not mistaken, in 2001. So the story is that Claude was in the middle of giving a lecture to mathematicians in Princeton when the door in the back of the room opens and in walks Albert Einstein. So Einstein stands listening for a few minutes, whispers something in the ear of someone in the back of the room, and leaves. At the end of the lecture, Claude hurries to the back of the room to find out what the person that Einstein had whispered to, what the great man had to say about his work. He had asked for the directions to the men's room. So, I mean, this is to show that he had a very self-deprecating sense of humor too. So, okay, so that's much on Shannon. So what am I going to do today? Well, as promised in my title, I'm going to give 5 personal research threads following down the pike. So I'm going to talk about duality between source coding and channel coding with side information, with and without. Most of the time without, actually, because it's going to be a tutorial. Chapter 2, encryption and compression. Chapter 3, sampling below the Nyquist rate. And Chapter 4, learning. And Chapter 5, codes for distributed computing, depending on how much time we have. Okay, we'll play it very relaxed. So the first chapter is on duality. This is not your convex optimization stuff. This is duality between source and channel coding. It's a different kind of duality, but a duality nonetheless. Okay, so this is joint work with Sandeep Pradhan, who's a professor at Michigan, and Jim Chow, who's at Apple. So we'll start again. So there will be a lot of references to Shannon's work. So Shannon's celebrated 1948 paper. This is the famous block diagram that launched digital communications, the digital era. And he characterized the general theory of communication, and he viewed it as a source channel destination problem. And the key idea was he didn't care about the meaning of the source. He abstracted the concept of a message. Just one of many messages. The semantics don't matter. Of course, in today's age, I don't know how relevant it is, but nonetheless, the concept was very profound. And you would send it and receive it at the other end, and there's a noise in the middle. And of course, he did source coding, and he introduced the notion of entropy, which we all know for discrete sources is expected value of the log of 1 over the probability. And so that's the fundamental limit on the compressibility of a source for IID. Then he, of course, extended that in 1948 to rate-distortion theory, where he characterized the notion of mutual information, which you all know, some of you know, which is h of x minus h of x given y. H of x is the source, y is a quantized source. So if you satisfy a distortion constraint, and the distortion measure is very important in what to follow, so make note of that. For a particular distortion measure, if your expected distortion measure is less than some constraint d, he said the minimum rate is the minimum mutual information between x and the quantized version of x. So what is the minimum description of x such that you still meet your constraint? So this is rate distortion theory. Again, make note of the distortion measure. In channel coding, of course, it's much more popular. He characterized the capacity, which is the maximum of the mutual information over all input distributions. So by the way, in the source coding problem, you have an optimization problem is you want to minimize over all conditional distributions of the quantizer given the source, right? It's also called the inverse test channel, reverse test channel. Here, you maximize over all inputs to the channel, and you maximize the mutual information, the amount of information y carries about x. And again, key is that there is a cost measure. Even if we forget it, don't forget that there's always a cost measure in a channel coding problem, which is the cost for using whatever symbol you put at the input. That comes with the W measure, and that has to satisfy some expected average constraint. And he showed that for rates R less than C, you can get essentially reliable communication. And this was quite a revolution at the time, because it used to be thought that rate had to go to 0 if you wanted perfectly reliable, or almost perfectly reliable. So we shouldn't kind of dismiss the fact that this was breakthrough, because at the time, linear filtering was the theme of the day, like Wiener filters. So they would remove the noise, kind of like analog communication, right? But Shannon kind of shattered that. He said that you should be designing code books, and you should be doing nonlinear estimation, which is the MLE at the receiver. And that will allow you to achieve transmission rates approaching the channel capacity. Okay, so now I want to give a few quotes of Shannon, which will be tied into the work we'll be talking about. He mentions in his paper, in 59 paper, that there's a curious and provocative duality between the properties of a source with a distortion measure and those of a channel with a channel cost measure. Okay. And this duality is enhanced if you consider channels in which there's a cost associated with different input letters. This is the cost measure. And it's decided to find the capacity subject to a constraint that doesn't exceed it in an expected sense. Then he continues, this duality can be pursued further, blah, blah, blah. And then he says, these are deep words. I just cite them because I like them. They have nothing to do with this lecture. But thus, we may have knowledge of the past, but cannot control it. We may control the future, but may not have knowledge about it. So think about it. It's pretty deep. Okay, now back to reality. Functional duality. So what are we going to talk about? Well, source coding and channel coding, just to clarify what are the maps for source coding, you have a source coming in, probably continuous valued, and it could be continuous or discrete, but the output is bits. The currency is always bits. At the decoder, bits come in and quantized representation of the source comes out. Channel coding, this is the message, which is bits, and it's encoded into a channel input. And the decoder's channel output, this is usually discrete, and this is continuous because the channel is usually continuous, and it spits out hopefully the same message that was intended at the source. So the functional duality I'm going to talk about is about swapping these two, okay? Meaning the channel decoder becomes the source encoder, and the channel encoder becomes the source decoder. So when is that possible? When is the optimal encoder for one functionally identical to the optimal decoder for the other? Okay, so this is what I mean by duality. Okay, stop me if there are any questions so I can clarify them. Okay, so for the next few minutes, I'm going to take you down kind of a toy example path. In fact, there's going to be a lot of examples in this talk because I think that's how you learn, with examples. And in particular, I want to hit on some of the key insights which will be clarified with these examples, okay? So bear with me. So let's go to the channel coding problem first. You have a message to send. It's an R-bit message. And I'm going to consider the BEC, the binary erasure channel, the most simple channel model. But it's a deceptively powerful model. The reason is that today's internet is really a BEC, or it's actually packets, but it's not bits, but they are packets. But nonetheless, the abstraction is the same. Packets either get received or they get dropped. And the receiver knows when they get dropped, okay, because the network informs them. So this is a really good model in case you're studying hard problems. Always boil it down to the simplest thing and study it. So the BEC is a good model. Just I wanted to expand on that. So in this problem, of course, the BEC is a memoryless channel model. Every bit either gets erased or not, right? So here's the model. A 0 comes in. Either a 0 comes out or a star. Star means got erased. Same thing with the 1. And the probability of being erased is p, and the probability of being not erased is 1 minus p. So in the channel coding problem, you want to send a message, and you want to receive it, and you want to, the key point is that you want to find how big a message can you send if you have, say, n uses of the channel. And to make that more formal, remember the cost measure we alluded to earlier. So let's say that we'll be concrete. We'll assume that the crossover probability is 20%, 0.2. And the cost for sending a 0 or a 1 is the same. It's 1 unit, $1 or 1 rupee or whatever your currency is. And the total budget is $10,000. So you have $10,000. You have to send bits over the channel. A 0 and a 1 both cost $1. So you don't need to discriminate. It makes the problem easy. But 20% of the bits get erased. So everybody agree with the setup? Okay, this is the setup. Okay, so the question is, how big a message can I send? Shannon's result was, it's 1 minus p bits per channel. This is the BEC channel, right? So I'm going to try, since this is a school, I'm going to prove to you that this is 1 minus p, but with some leeway, that no epsilon deltas, okay? We'll throw that out the window, but you'll get the main insights. And we'll first show the converse, so you don't need Fano and all that complicated stuff. It's a very simple proof of converse. The forward part is slightly more complicated, but nonetheless. So what is Shannon capacity? Let's see how we derive the converse. So show that it cannot be more than 0.8, right? Well, here's what we're going to do. Remember, this is an erasure channel, which means the decoder knows which bits are erased. That's what the channel model is. He knows the stars from the zeros and ones. So the decoder knows that the 3rd bit and the 5th bit got erased. They're stars. That's the channel output. So let's assume the presence of a friendly oracle or genie that informs the encoder also before transmission that the 3rd bit and the 5th bit got erased, right? So you're told, and of course by you know that a p fraction are going to get erased, but the decoder informs the encoder. What does the encoder do? Well, the best the encoder can do is what? To dodge those starred bits, which we know that are going to get erased, and send information in the non-starred bits. That's nothing else you can do. So that will represent, if you have $10,000, it'll cost you 8,000 non-erased bits, because you know, with high probability, this is law of large numbers, that 2,000 of those 10,000 bits are going to get erased with high probability, right? So that means 8,000 is the maximum number of non-erased bits. That means we know that the capacity for the DEC cannot exceed 0.8. This is the proof, right? Very simple proof, which you can teach to undergraduates, which we do, actually. So you don't need very advanced techniques for that. But that's because it's a simple model. So surprising thing, because of Shannon's creation, it turns out the encoder does not need to know which bits are erased. So Shannon's magic says it's as if the encoder knew, the same effect. Okay, so if you think about it, that's pretty profound, right? How he does that. Well, how does he do it? Random coding. So this thinking pretty outrageously out of the box, he said, let's do the following. Let's design a code book that encoder and decoder will share, and we will populate the code book with entries which are drawn from random coin flips, Bernoulli half. So encoder and decoder have to agree on this random code book, so they know both the code book. And I'm going to have 2 to the 8,000 of such random entries, and it's a 10,000 channel uses, so it's 2 to the 8,000 by 10,000 matrix of random numbers. So I'm going to color code this. The encoder operation is in red. What is the encoder going to do? He's going to get a message which comes in from the left, and he's just going to, so this is the message that the channel wants to send, and he just spits out whatever entries came out, and that's my channel input. That's what I sent. The decoder, on the other hand, this is generically, he will get a received bit stream from the channel, and he will map it from the right. You look to see which of these 2 to the 8,000 code words is the closest to the received code word in whatever sense, the distortion sense, usually Hamming distance in this example. And he'll spit out the left-hand side as a message. So encoder is red, goes from left to right. Decoder is green, goes from right to left. Okay? So make note of that. And why does the BEC capacity 1 minus P, right? So let's kind of make it more generic. So let's say there are n channel uses and 2 to the nr of these code words. This was 8,000, 2 to the 8,000, and 10,000 in the example. We'll note that P is 0.2 and N is 10,000, right? So let's say you want to send message 3. You just spit out this bit stream. That's the encoding operation. So that's what goes in. What does the channel do? The channel is going to erase 20% of those bits, right? That's the BEC. And let's say that it erased the last 20,000 of the 10,000, rather. What did I say? 2,000 out of the 10,000. Right, thank you. Because I don't want to, in general, it can be anywhere, but without loss of generality, we'll make it the last. Nothing changes if you make it any other pattern. So what is the operation for the decoder? The decoder now has a truncated codebook, right? Because the codebook was 10,000 long, now it's 8,000. In fact, it's n times 1 minus p. But it doesn't have access to the other 2,000 bits because they were erased. So it has to look in the truncated codebook to see which message was sent, right? Now you know that the actual message that was sent, the first 8,000 bits, have to occur here because they were unerased. So you know that the correct message is there. So the only time you will make a mistake is what has to happen for you to make an error. If you know you sent something, which is this guy, when will the decoder be confused? Yeah? That's right. When there is at least another extra code word that looks exactly the same, and the decoder says, what is this? I don't know what's going on, right? Okay, so that's what happens. So you see that the decoding is successful if the non-erased string is unique in this code book. Now, what is the probability that you're not unique? We'll do the opposite argument. You can show, it's very easy, because if you compare, let's say that the message 3 was sent, and what's the probability that message 1 looks like message 3? Well, how many bits are there? N times 1 minus p. What's the probability that 2 bits are the same? Half, because this is Bernoulli half. So what is that probability? It's going to be half to the n times 1 minus p, or 2 to the minus n1 minus p. This is the probability that the first and the third match. Okay? But there are 2 to the nr of them by union bound, right? So there are 2 to the nr confusing, possible confusions. So this you can see very simply that it will go to 0 if and only if r is less than 1 minus p. So this is the achievable part, which with epsilon and deltas can be made more precise. Okay? So basically it's saying that if I'm not too greedy about sending more than 8,000 bits, then I will be successful as long as 2 to the 8,000 will make sure that I have only one unique match. Okay? Okay, so this is the general principle of, so we just proved the BEC. Okay, this is a school, so we showed a converse, we showed the forward part, agreed, we hand waved a bit, but for the most part, these are the insights. Okay, what is the source coding dual to the BEC? It's a strange quantization scheme. It's something known as the BEQ. Okay? This turns out to be the exact dual of the BEC for source coding. What is that? Again, we start with 10,000 bits at the input, and 10,000 symbols, not bits. Now your symbols consist of 3 alphabet of size 3. You have zeros, ones, and stars. You got to have stars somewhere, right? So the stars appear at the input here. Okay, and we're going to make the probability of stars be 20%, just like we had 20% erasure in the other problem. And we're going to make zeros and ones equally likely in the other 80%, so 0.4 each. And the compressed bit stream is going to be 8,000 bits. And the source decoder is going to find you want the average distortion to be less than or equal to 0.2. So remember, this is a rate distortion problem. You cannot tolerate this is a Hamming distortion measure. Actually, it's not. I'll show you the measure. The measure is it's a very strange quantizer. So this is the input, this is the quantized version. If I send a 1, if I reproduce it as a 1, there is no penalty. The cost is 0. If I send a 0, if I represent it as a 0, again, no penalty. If I send a star and I represent it as either a 1 or a 0, I have 1 unit of distortion. Okay? So I get 1 unit. But if I confuse a 0 for a 1 or a 1 for a 0, I'm infinitely punished. So you cannot afford to do that. So if you want to keep the distortion to a finite number, you have to make sure that you don't screw up on the zeros and ones. They have to remain intact. But you have the freedom to make the stars anything you like, because you will be charged the same 1 unit of distortion. So everybody understand the measure? So note the measure is very important. It's not Hamming. It's this for this duality. Okay, so that's what I wrote here. So star is like a don't care. And just as a practical kind of motivation for the star, which is the don't care, which is like a wild card, it could represent a perceptually masked symbol. For those who have done audio or image processing, you know that some samples can be masked by their surrounding samples because of tones and so on. So you could imagine that the encoder knows where the tones are, so it masks those stars. But the decoder doesn't know, right? So that's the situation here. Okay, by the way, this was also studied by Martinian and Yedidia in 2004. Okay, so now how do I show that the BEQ and the BEC are duals? Well, we'll put it to the test. Well, before we do that, let's prove that the BEQ is going to give you, will give you 8,000 bits as your compressed bit stream. So the claim is I can take 10,000 bits symbol stream and compress it to 8,000 bits, right, with a measure of 0.2. Okay, so again, same, even the story of the converse is a dual. Okay? So in what sense? Well, you know that the encoder knows which are the starred bits, right? Because it knows these bits, these locations are don't cares. You can do whatever you want. You can assign them zeros or ones. Suppose it passes that information to the decoder as well. The decoder also knows stars where they are. So then what is the best encoding strategy? If you have 10,000 bits and 2,000 of them are stars, and the other 8,000 are zeros and ones, what is the, and you cannot afford to screw up on them, right? You have infinite distortion if you mess up a 0 for a 1 or a 1 for a 0. So what's the best strategy? Just send it, yeah. Basically just send the non-starred bits in the other locations. Because even though, so you basically take the bits, even though there are stars punctuating them, you just send the bits in right order. The decoder knows how to write the punctuation because it knows the stars. So it got 8,000 bits. So you compress this 10,000 stream for 8,000, and you can't do any better. So again, in this case, it's 8,000. So you know that the rate distortion limit of this, meaning the BEQ rate for a distortion of 0.2, cannot be smaller than 0.8 bits per symbol. That's the maximum. Okay, so this is the converse. How do you achieve it? Okay, surprise is, again, the decoder does not need to know where the start symbols are. It's as if Shannon's scheme will allow you to discern it implicitly, just like we saw earlier. So what's the source coding dual to the BEC, the BEQ? So how do you do it? Well, the same theme. Swap the encoder for decoder and decoder for encoder of the BEC, and you will get, voila, the BEQ. Okay? It'll work. Why does it work? Again, I want to recall the Shannon's prescription of the random code. Highly impractical, right? But conceptually really rich. So again, you have your code book of size 2 to the 8,000 by 10,000, random Bernoulli half. Encoder and decoder agree, and then I want to remind you that the red was the encoder going from left to right, and the green was the decoder from going from right to left. Now we have to swap the roles. So that means the green is now the encoder and the red is now the decoder. Okay? So that's what it is. So now the input is going to be this bit stream, which is the source, and it gets quantized to a message. This is the quantization index. And at the decoder, the quantization index comes in, and out comes a representation. So let's calculate this carefully for the BEQ example. So you have, again, you have IID Bernoulli half. This is the code book for the source coding. It's the same code book. It's the same random coin flips that the channel coder was using there. Borrow it. Use the same code book. And you have a bit stream of length 10,000. As I said, half 40% zeros and ones and 20% stars. And again, without loss of generality, let's shove all the stars to the end to avoid clutter, because it's all memoryless anyway. And recall that P is 0.2 and N is 10,000. There's 10,000 symbols in the stream. Now, what happens? The encoder is faced with having to find a message corresponding to one of these 2 to the NR code words, right? Because again, these NP guys are stars, so they don't matter. But you have to make sure that you faithfully represent the first 8,000 bits of the message, because you'll get infinitely penalized if you miss even one. So that means, what is the time, when will, remember the encoder is now doing the hard work in source coding. So how does the encoder make a mistake? If I'm given a stream, say source puts out this stream, how can the encoder make a mistake? In the other one, there was a notion of uniqueness, right? So what is it for here? You have to find a match. You better find a match for every stream you input. So in this example, there happens to be a match for this guy. But in general, if you couldn't find a single code word for which there is no exact match, you are infinitely penalized, you're out of the game, right? So you can't do it. So you have to find a match. So encoding is successful if there exists an exact match for the non-start part of the bit stream. Now you can go through the calculation one more time. Very simple calculation, probability, elementary undergrad probability. What's the probability that you don't have an exact match? Well, this is the probability that you have an exact match. That, again, like before, 2 to the minus n times 1 minus p is the probability that you have an exact match. 1 minus that is the probability you don't for one code word, but you have 2 to the nr code word, so you raise it to the 2 to the nr. And you can show this goes to 0 if and only if r is greater than 1 minus p. Okay? So this is proof of achievability, meaning 8,000 source bits will induce an exact match with high probability if the random codebook is of size at least 2 to the 8,000. Now, note now, it has to be on the other side. In the channel coding problem, it cannot be more than 2 to the 8,000. Here it has to be at least 2 to the 8,000. Because if you have more, you might have some duplicates, and you will certainly have a match. You may have many matches, but that's okay. In source coding, that's okay, because it's a covering problem, right? Whereas channel coding is a packing problem. Okay, this is tutorial here. So if you're not following what I'm doing, don't worry. It'll change. The weather will change. So knowledge of the erasure pattern. So what is the duality here? Again, I want to recall to you, in the channel coding problem, the encoder didn't know something that the decoder knew. Whereas in the source coding problem, the decoder doesn't know something that the encoder knew, but it's as if you don't know it, no problem, right? It can still work. Of course, at the cost of this very humongous complexity of codebook and so on. But still, conceptually, it's very powerful. And then, of course, channel codes have come a long way in trying to bridge the gap between theory and practice. Okay, so what is the duality statement? I'm going to be very high level and informal here. So it turns out that given a source coding problem with a source distribution, Q of x, output quantizer P star of x hat given x, and this is the quantized x hat probability. All you have to do for finding the channel coding problem is swap the arrows. All the arrows going right now go left to right, go right to left. So P star of x hat is the input, Q of x is the output, and the channel is the reverse of this, which is found by using Bayes' theorem. Instead of probability of x given y, you find probability of y given x. There are some details I'm not going to bore you with, but it turns out that if you're given a source coding problem with a source distribution and a quantizer and a distortion measure, very important, the distortion measure, and an average distortion constraint D, there exists a dual channel coding problem with channel, the flipped version, P star of x given x hat, and cost measure W of x and cost measure W, such that the rate distortion for one is a capacity cost for the other. They're both at the limit. And the cost measure has to be very carefully tuned to the problem. So in particular, you can show that it has to be the Kullback distance between P star of x given x hat, which is the channel, and Q of x. So in some sense, it has to look like the average. Then you have low cost. If you look very atypical from the average, which is Q of x, you would be penalized. So that's kind of the intuitive feel, but there are some details. But you won't go through it. But the key takeaway is that for any given source coding problem, there is a dual channel coding problem, such that both problems first induce the same joint distribution, and the optimal encoder for one is functionally identical to the optimal decoder for the other, provided you have an appropriate channel cost measure associated with the channel coding problem. Matched to the source coding problem. So key takeaway, which is often lost, is that in a source coding problem, the distortion measure is as important as the source distribution. It's not enough to tell me what's the source distribution. You want to tell me what's the measure. Is it a mean squared error? Is it L1? Is it L infinity? It's very important. Likewise, for channel coding problem, the channel cost measure is as important as the channel conditional distribution. So if you're given a channel, you can find the capacity, but implicit in that is that you're assuming a cost measure. And that implicitness has to be made highlighted. So that's what this kind of work summarizes. Okay, so I took a lot of time. This was the basics part. So this is a tutorial. This has nothing to do with what's going to come. But nonetheless, I thought in an IT school we should give some basics of info theory. So note that I gave you two proofs, both converse and forward, right? And so that's more than you do in information theory lecture, right? I mean, since when did you get 2 complete proofs for anything, right? The BEQ allows you to do that. Okay. All right. So now let's move on to side information. So, well, this is, I'm going to abbreviate it as SCSI or SCSI, which is source coding with side information. So you have an encoder and decoder. The typical example that's given is the sensor network, or IoT as they call them these days, right? So you have X and S are 2 sources, and you want to quantize X in the presence of S. So let's say S is available at the central fusion unit at encoder and decoder, and you want to compress X, and let's say everything is discrete. So the rate that you need to expend is going to be the conditional entropy of X given S, since S is available at both places. So now what happens if S is not available at the encoder? So this is the Slepian-Wolf problem. So if only the decoder has access to S, there are many applications which are given here. Interestingly, under many conditions, there is no performance loss in some important cases. In other words, it's as if S was available at both ends, even though S is available only at the decoder. Okay? So what are those cases? Well, before we do that, let's find the dual to this source coding with side information problem. It's called channel coding with side information. It's called CSI. So here it was like sensor networks and upgrade and so on. Here, the idea is that, again, you can have source available at both ends or only at the encoder. And this has been studied in the literature by Gelfand, Pinsker, Costa, Higard, El Gamal, big names in information theory. And the applications are data hiding, watermarking, writing on dirty paper, MIMO broadcasts. So there's a lot of applications. They're kind of underrated kind of problem. And again, there are no performance loss in some important cases. So I'm going to kind of highlight the fact how is it connected to watermarking, just high level. Well, remember, you have a message to send, and the message you're going to send is you. There is a side information, which is the host. Okay, remember, in watermarking, there's an image or video or audio or something, and you want to embed some pattern on top of that to identify that source is whose source that is. So that embedded pattern is the M. And you're going to embed the U is a signal version of M, on top of the S, but you have to make sure that you don't distort the S too much. Otherwise, it's going to be not useful. Because the host is modified too much, then what's the point? I mean, you watermarked me, but you completely killed me, right? You can't do that. So basically, there's a constraint on how much distortion there is between S and X. Is that clear? Because U cannot be of very high power. And you, at the same time, while you satisfy this constraint, and in addition, there's a channel noise, which is common to the problem, you need to be able to extract the watermark at the decoder. That's M hat, successfully. So this it's also related to steganography, and there are other applications. But now, 3-bit example, okay? Remember I said we'll just stick to toy examples, which will highlight the point. So how does binary compression, noiseless compression for the SCSI work, which is source coding with side information? We'll consider the easy case first, kind of like converse, okay? I'm going to give you 4 proofs, okay? 2 on duality and 2 on duality with side information. So here's suppose I have a 3-bit source, length X and S. X and S are 3-bit equally likely data. And the Hamming distance between X and S is at most 1. So this is the source coding problem. So X and S have at most 1 bit off in their 3-bit representations. So for example, when X is 0, 1, 0, S can be the same or off in the last bit or middle bit or first bit, right? All equally likely. So how many bits does it take to send X if I know S at both ends? This is the easy part. What do I do? I mean, I've put it down there. What's that? No. You're overcomplicating. You're thinking too much. I have S here, and X is at most 1 bit off from S. Yeah, send the bit that's different. Yeah, and how many bits does it take to index? Which bit is different? Log 3. No, remember, it could be the same. I said the distortion is up to 1, right? So there are 4 patterns, right? Basically, what you're saying is they could either be the same off in the first bit, second bit, or third bit. And there are 4 patterns, all equally likely. You index them with 2 bits, right? Log of 4 to base 2 is 2. So that means I need 2 bits to tell the decoder which the X was. Okay, now comes the complicated one. What do I do when only the decoder knows the S pattern and I want to still send it at 3 bits, at 2 bits? So I already showed you the answer. If you didn't peek, or if you didn't understand when you peeked, we are still on. So can I compress X at 2 bits, even though the encoder doesn't know X, but the encoder does know that X and S are at most 1 bit apart. So what do? Any ideas? Including those who know. Okay, so the idea is that, okay, the key is looking at this bin, okay? So when X is 0, 0, 0, or 1, 1, 1, 3 zeros or 3 ones, what are all possible S patterns that could have happened? When X is 0, 0, 0, S could be one of these 4, right? With at most 1, 1 in its tree. When X was 1, 1, 1, when X is 1, 1, 1, S can be in the bottom half. And they have at least two ones. What do you notice about this right-hand side? They are mutually exclusive, right? So you cannot have both this and this. Only one of them can happen. The other thing you notice is that between them, you exhaust all of possibilities. There are only 8 3-bit possibilities, and they're all exhausted. So you're in a good situation where I've exhausted all possibilities, and they're mutually exclusive. What does that mean? The encoder should not waste any bits in trying to distinguish whether a 0, 0, 0 or a 1, 1, 1 happened. Right? That happens with probability 1/8 or whatever. Okay, so what do? Well, you bin that. You call that you have a bin consisting of 0, 0, 0, 1, 1, 1, and you follow all its offsets. Likewise, 0, 0, 1, 1, 1, 0, 0, 1, 0. All these 4 cosets or bins are all going to be equally likely, and they all capture what the encoder wants to send. So it should not spend 3 bits on that, but only 2 bits, the label of the coset. So this is the key idea of Slepian-Wolf. Okay? So transmission is still at 2 bits per sample is achievable. Encoder sends the index of the coset containing X, and the decoder finds the code word that is closest. So for example, if X is 0, 1, 0, then you know that the encoder has to send 1, 0, this pattern, right? And how does the decoder do? The decoder decodes the S to the closest index, and it recovers the 3rd bit. Okay, this is the key idea. Okay, what about channel coding with side information? Okay, wow, head is reeling now, right? So remember, this is the problem. And what is a 3-bit example in this case? Well, we're going to assume that the host is a 3-bit uniformly random signal. So, for example, binary fax signal. Okay, this is just a toy. The message is the bits to be embedded in the host signal. Remember the watermark. And you're allowed a maximum distortion of 1, which means that, remember, we cannot distort S too much. So X and S can be at most having distortion 1, okay, at most 1 apart. Okay, so I'm going to eliminate the channel because it's a 3-bit example. You have to give me a break. I can't cover everything with 3 bits. So Z is gone. So let's say it's noiseless, but you still have the distortion constraint. So it's a clean channel, so Z is 0. And case 1 is when both encoder and decoder have access to the host signal. So let's say both of them know the host signal and you want to communicate one of these bits. That's an easy problem. You can just same deal because U can only be one of these 4 patterns, all the patterns which have having the weight of 1. 4 of them, each equally likely, so 2 bits. So I can send 2 bits through this channel if both of them have the S. But what happens if only the encoder has access to S? That's the deal with the channel coding with side information problem. So same deal. So it's the same thing that we saw earlier. How can we still embed a 2-bit message while satisfying the fact that X and S can be at most distortion 1 apart? Same deal. You use the same code book that you use for the source coding with side information problem, and you index them 0, 0, 0, 1, 1, 0, and 1, 1. For example, when S is 0, 0, 1, M is 0, 1, this index. So what is the key here? The code book is partitioned into 4 cosets. Each of these cosets, each of the 4 messages indexes a coset. Now, the problem is that the encoder has S. It nudges S to the closest entry in X in terms of its weight. So for example, when S is 0, 1, 1, and this message needed to be sent, then 0, 1, 1 will be quantized to 0, 0, 1, which is within distortion 1. You'll see that no matter what message was intended and what the side information was, because of the partitioning, there will always be one entry which satisfies the distortion constraint. For example, this is for 0, 1, 1. What if it had been 0, 0, and 0, 1, 0? Well, that would be 0, 0, 0. So you can check it. All cases of independently, whatever message you want to send and whatever source you had that you want to embed in, you will satisfy the constraint. Okay, so this is the summary of the duality in the more complicated side information case. So you have source coding with side information encoder becomes a data hiding decoder, and data hiding encoder becomes a source coding with side information encoder. Okay, I know that I've covered a lot, but the key is that the code book is identical for both problems, and you index them with the coset pattern. But in the channel coding problem, ironically, this becomes a source code, and in the source coding problem, it becomes a channel code. Okay, it's all mixed up. Okay, so loose sense, what's going on, high level. Fuzzy problem, this is a channel coding problem, side information only at the encoder or at the decoder. Here the channel code is partitioned into a bank of source codes. That's why you can nudge it to the closest source code entry. Here the source code is partitioned into a bank of channel codes which have distance. So the decoder can recover. And there are some very important cases in which there is no performance loss. That is, even if both sides had the side information, you could do no better. So this is the much more general form of the duality. I'm not going to bore you with this. There's Markov chains flying left and right, and there's duality and so on. Okay, but I'll spare you. But if you understand the 3-bit example, you'll get most of the point. So the key is these two problems are functionally identical. So if you make progress on one, you cannot help but make progress on the other. Okay, so it's like 2 for 1. Buy one, get one free. Okay, and all these applications, therefore, must be intellectually the same thing, intellectually united. So this was pretty cool when we discovered this. So this is kind of the spirit of Shannon, because Shannon saw there was duality. And this is duality taken to an extreme, right? Okay, so that's chapter 1. How are we on time? This is a very short chapter. Let's do this. Okay. This is also an interesting chapter. So now you can wake up. Okay. I bored you with a lot of stuff. I sprinkled in a lot of toy examples to try to keep you awake, but I understand lunch was less than an hour ago. So, okay, cryptography. Okay, this is Prakash is sitting there. He was one of the co-authors when he was a postdoc at Berkeley. Man, I'm feeling old. Okay, so foundations of modern cryptography. This is a paper by Shannon in 1949, where he describes the communication theory of secrecy systems, and he talks about the fact that to have information theoretic security, you need the concept of a one-time pad. That is, for every bit you want to send, you need one bit of key, right? You need the key to be at least as long as the size of the message you're sending, which is totally impractical, and that's not what the computer scientists do. Because they go for computational security, which is more practical. But nonetheless, if quantum computers ever come to being, you need to worry about this. So don't forget about the information theory part. Okay, so I'm going to engage you in a particular exercise where I'm going to compress and encrypt. So this is compression of encrypted data. So the x is a binary input. Let's keep it very specific. I can compress it to its entropy h of x. And then having the one-time pad, the cryptographic key, I can encrypt it so nobody can understand what's going on, what the source bits were. And that will be encrypted and compressed. So more precisely, if you want to imagine, think of the source as being a Bernoulli 0.11. It's chosen on purpose because the entropy of Bernoulli 0.11, as we know, is a half. Okay? That's the only thing I know. Okay? I know if you put a Bernoulli 0.11, the output entropy is a half. So I can compress this for half a bit per symbol. If I encrypt that, well, I'll be both encrypted and compressed. So I'm both. Remember, if this is sent over a network, the network provider wants efficiency. That means he doesn't want you to send useless bits. So you should compress it. But this is the user. He doesn't care about whether you compress it or not. I just want to make sure it's private. I don't want anybody peeking into my bits. So he wants to encrypt it. So, question. Can we reverse the order of these two modules? Can I first encrypt from x to y and then compress? What do you mean and then compress? This is a random bit stream, right? In fact, when we published this, there were blogs in the popular press type thing, which were kind of maligning this work, saying, what is this nonsense? How can you take random bits and compress them? That's totally unintuitive. And then they went on, and it was pages and pages. I mean, it was very amusing to follow them. Nonetheless, under some conditions, this actually can be done. I can actually reverse the order of compression and encryption. I don't know what the applications are other than what I just said, where, potentially the user doesn't care whether you compress or not. He doesn't want to burn battery power doing his encryption, rather his compression, but so he encrypts it. But the network provider is very interested in saving bits. But the user doesn't trust the network provider, so he wants to encrypt it right at the source. Okay? So there might be applications and cameras and so on, but we didn't pursue that. Okay, so the key is, if we did this, the encryption and compression, encrypted uncompressed data will still be at 1 bit per symbol because I didn't touch the compression. But supposedly I can still compress and encrypt at 0.5. How do we do this? What's the magic? I already explained the concepts of leading up to this, so you should be able to tell me. This should not be a mystery to you. What problem does this remind you of? An unsolvable one? Okay, before we do that, let me show you a demo that it really works. Okay? So this is Dilbert, 100 by 100 image. The entropy of this is not half a bit. It's much less. Okay? But you have to give me half a bit, okay? Because I'm showing you a demo. So this is 10,000 bits I want to send, and this is not IID, but assume it is. So here's the encrypted image. So the compressor is faced with compressing this encrypted image. Looks like white noise, right? It should. A good encryptor will give you that. But he's going to throw away very bravely half the bits. 10,000 bits become 5,000 bits. And the claim is the decoder is still going to work. And here's the decoder in action here. It turns out that it was using an LDPC code, the low density parity check code. You never thought they would come into this problem, but they do. And the final reconstructed image is indistinguishable from the original image, even though I threw away half the bits. How did I do that? I'm not a magician. I'm not a bullshitter. So what is it? Okay, that's the problem, right? How did I throw away half the bits from 10,000 to 5,000 and still make it all work? Well, the key is the key, okay? The encryption key is the key, okay? Let's look very carefully at what happens. in the reversed order problem, X comes in, it's encrypted by this key, and Y comes out, and this encoder is the network provider's device. It has no access to the key, so it has to compress Y to something else, right? But what is the key is that at the receiver, clearly the user will have a decoding key, right? Otherwise, you can't decode the encrypted image. The fallacy in thinking, why you're fooled into thinking this is impossible, is that you have a very sequential way of thinking, right? We are used to that. You're saying, oh, compressor, encryptor, decryptor, decompressor. Or encryptor, encoder, decoder, decryptor. But the key is that this decoding and decrypting can be done jointly. They don't have to be done sequentially. If you do them sequentially, you're right. I couldn't have done this. It would have been magic. But if I do them jointly, you notice that what is common between the user and the receiver is the key. So that is side information, exactly like Slepian Wolf, what we just saw a few minutes ago. So Slepian Wolf can send, so we know from the theorem, and also the 3-bit example as an inspiration, that I can, even though the encoder doesn't have access to the key, he can compress the encrypted source as if he did. So that's why, which is a conditional entropy of Y given K. And that's why it works. And this, some more details. Now, this is a review for what we did from the last time. Now, the key is the 3-bit random key. X is the uniform source. And again, the case where key is known at both ends is very trivial. You just index whatever was sent, and then you subtract and add and subtract at encoder and decoder. Now, because of the Slepian-Wolf theorem, you know that the key, again, is exactly, key is like the side information we saw in the other case. So you break up Y into these 4 cosets, or you can think of it geometrically as this cube. So basically, you make sure that only the diagonal entries form a bin. So 0, 0, 0, and 1, 1, 1 are opposite diagonals, if it's a room. And so are the other 3. And instead of sending the entire 3-bit, you only send the index of the coset containing X. So that's how you get your compression. So you can compress encrypted data. So for example, when the Y is 0, 1, 0 and the key is 1, 1, 0, you know that you have to send the message 1, 0 because this was the Y. And the key was exactly within 1. So a more geometric picture of this, in case the 3-bit example confused you, this is much more graphical and illustrative, is what are we doing here? We are compressing Y as X plus K. Y is encrypted. And X is unencrypted and compressible, right? It's uncompressed. And that is X plus K. So Y is this. So let's say I want to quantize Y to this resolution of these small balls. And everything fits in the big ball. So this is your Gaussian type of picture. So I need to compress star, the index Y, to the resolution of the small balls inside the big ball. So in this example, it's that purple ball right there, near the red, right? So what the Slepian-Wolf theorem is telling you is that you're going to signal to the decoder. I'm not going to tell him which box exactly my source fits in, but I'm going to send the color of the box that it fits in. So in this example, it's this purple, right? So at the decoder, he gets the purples are all over the place. But he also has side information, which is the key, which is closest to the correct purple. So you don't have to spend bits in distinguishing, which purple. That's where you save the bits. But you just send the color information. It's a purple, it's a red, it's a blue. You will figure out which one. Okay, so this is the key. Okay, so practical code construction. So we have built on this, and we use a linear transformation or hashes or bins to design cosets to have maximal spacing. And at the time, we were using LDPC code. There are better codes available these days, but that's unimportant, which code you use. The fact is that you can use a code to make this work. And this was formalized in the form of a distributed source coding using syndromes, or Discuss. And the source code words are partitioned into bins of channel codes. and you only indicate the color. You only send the color, and the decoder will figure out which color. Okay, which entry in the color. Okay, so, yes?
So what do you need to tell the service that is in, what information do you have to give him in terms of, for him to do the compression?
Well, yeah, I didn't tell you. He has to have a notion of what is the entropy of the underlying source. And yeah, I mean, he's not going to get perfect. It's not going to be like a Lempel-Ziv type thing. Okay, it's not going to be perfect. But given that I'm compressing encrypted data, anything seems pretty good.
So it's like you're coding and you're asking him to add an error, but you design.
No. There's no errors. This is source coding. Okay.
No. I know, but I'm saying, but it's sort of equivalent to you asking him.
You have to know how many bits would have been enough had you had the unencrypted data. You need to have an estimate. And we have extended some things in the case of video where you can estimate that based on the previous frame. Okay? You can actually do this for video. It's a pretty cool demo. You get a sequence of white noise-like patterns, and you compress them. And the key is that the first one, you kind of spend some bits, you learn, and then you use, you track what you learned to estimate the entropy of the next frame, and then you can keep doing this. So it's a cool demo. It definitely wows the undergrads because they see this and say, wow, what is it? Well, come learn information theory. This is why to learn. Instead of saying, oh, this is a Slepian wolf, here's the proof, here's the converse. No, give me a demo. Oh, this is cool. Where do I learn this? Come to information theory. Okay, so that's kind of the ad. Okay, so shall we take a break? Or, yeah, one more question?
You said at the beginning that this is different from the cryptography that computer scientists do.
Yeah, because of the different. Okay, there is no real difference. Computer scientists can also do this. There's no problem. I forgot a little detail which had to do with how many key bits do you need. Okay, so this is beyond the scope of what I can do here. Let's go back. See here the key. So if you were astute, you would have observed the following fact. This key here has to be the size of this, right? Because a one-time pad. You need as many key bits as message bits. So the key's length is actually h of x in the ideal setting. In this setting, the key is supposedly working on x, right? So this is the longer sequence. It's the uncompressed. So the key has to be longer. So from an information theory setting, it appears as if this needs a longer key than this, and so you're really cheating. But it turns out that you can make the key also h of x with some mild assumptions. Okay? So the information theorist would say, oh, this is okay. The computer scientist wouldn't care, okay? Because he starts with the pseudo-random number generator from which he generates the keys. So it'll be his 32 bits. So yeah, anyone can use this scheme. Okay, so I have a question for you. Should I stop now or should I keep going? What is the timeline? Where's Bobak?
Yeah, it's 2:15 now. If we were to go like
Let's go.
one long break,
Okay.
then we would stop at 2:40.
Okay, fine. Let's keep going. Okay, the sampling. Okay, I'll tell you. I know where to stop. Okay, let's consider the sampling. So this is the part where sampling theory is addressed. So I'm going to sample and compute efficient, and this is joint work with Orhan and Simon Lee. And there are also connections to learning, which will be after the break. Okay. So sampling theorem. Remember, I keep referring to Shannon. Shannon had his hand on all of these. So he had a hand in sampling theorem, which is the Nyquist theorem, also known as. So Shannon, Nyquist, Whittaker, Kotelnikov all have their names on the sampling theorem, which is what? Communications in the presence of noise. So in his paper, he wrote about how if a function contains no frequencies larger than w cycles per second, it is completely determined by its ordinates given at half w seconds apart. So basically, you have to sample at twice the maximum frequency, right, for the real valued signals. That's the statement. And not only that, he gave an explicit formula how you interpolate from the sampled points to get the signal back. You do the sync interpolator. Everybody who has taken DSP should know this. If you haven't, welcome to it. And if you're still interested, carry on. But the key is it's a linear interpolator. Okay? I want to mention that. I want to stress the fact that in this sampling theorem, you do sampling and you do linear interpolation. Okay. What is the aliasing phenomenon? Well, again, you know from your undergraduate work that in the time domain, if you have that signal which has a bandwidth of, say, 1 hertz, then if I sample at the rate of 1 per second, I will just make sure that my replicas, which in the frequency domain, you get periodic copies of your spectrum. So if you just do enough, you will barely recover it by linear filtering. Right? You're sampling at the Nyquist rate. Now, if you're greedy and you sample at rate of half, then you will get messed up because these copies are going to overlap and you get junk. So this is to be avoided, and we've been taught instinctively to avoid aliasing at all costs because it's bad news. So please sample fast enough that you have no aliasing. Okay? Is that clear? This is just an intro thing. Okay, but things change considerably if the spectrum is sparse. Okay, so consider a gigahertz worth of spectrum, and these are all the occupancies in that 1 gigahertz. And if you added up all the spectral occupancies, it comes to 100 megahertz, which is 10% occupancy. It might be even less, okay, as we go to ultra-wideband. Okay, so this problem was also solved partially by Landau in 1967. It's going back a while. He said that if I know the frequency support of this spectrum, then it turns out I can sample at the rate at which the bandwidth is occupied, the frequency of the occupant. This is known as the Landau rate. But there is a hidden assumption here, is that I need to know where W1 is and W2 is and W3 is. Okay? That's the hidden assumption. And when you do not know the support, there's been a string of works, but to my knowledge, it remains an unsolved problem. Okay? When you don't know the support. There are existential results, and Feng and Bressler were the first to start it. Lu and Do, Michali, Eldar, and Massimo at UCSD also have done work on this. And to my knowledge, this still remains an unsolved problem from a constructive standpoint. Okay? There are known results for existence. So again, Landau's result is that you can sample at this occupancy rate, provided you know where the frequency bands are. Okay? So, and it's an existential result. That is, there exists a scheme that will work, that there is enough information in the samples that you're collecting. Okay, so we're going to go into a little bit of signal processing. So for those who are not familiar, there will be a little tutorial. And for those who are, maybe a review, or maybe, I don't know, whatever thoughts come to you. So input frequency, these are the input frequencies. You know the frequency support. And so this is the case of Landau. I know where the frequencies are, where the bands are. So what do I do prior to sampling? Remember, we've been taught never to alias. It's our instinct. So we put a filter around W1, and you get the red spectrum. You filter around W2, you get the blue spectrum and the green one. And then you have no aliasing thanks to filtering. So you can basically sample at the occupancy rate, right? This is one way to do it. But this is crucial to knowing where the bands are. So what about when you don't know? This is called spectrum blind. There's also a learning problem, right? I want to learn which are the bands that are not occupied. So it requires, it turns out that Lu and Do showed a non-constructive result, existential result, where they showed that in the spectrum blind case, you have a hit factor of 2 in the worst case. Okay? So 2 times the frequency occupancy will be sufficient to recover, but the proof is non-constructive. Okay, now I'm going to, whatever you do, if you're sleeping, wake up for the next 2 slides, because this is going to be the theme for the rest of the talk, for most of the rest of the talk, okay? And it's kind of fun, so it's a puzzle. So hopefully you wake up. Yeah, Tara? Adaptivity in what? you'll see that you don't need to be adaptive. I'll show you a scheme which is not adaptive. But nothing was known before this. Yeah. Okay, so I'm going to, so as I said, please wake up for the next 2 minutes and I'll engage you in a puzzle. It's about a gold thief. So I come from India and we used to read comics and we had all these characters flying around and they were amusing characters, and so this is one of them. Okay, so there's a gold merchant. The rich in India are very rich. Okay, so this is one of those very rich people. So he's got gold coins and they weigh 100 grams each, and he has 5 servants or treasurers or ministers, whatever you call them, and he gives it to them for their safekeeping. Okay, and unfortunately, one of those guys is a thief. You don't know who it is. So he steals an unknown but fixed amount from each coin. So this is important. So what the thief does is he takes a slice of each of the coins that he was given, and you want to find out who the thief is and how much he stole. Okay. So question, this is a recreational question. What's the minimum number of weighings you need to figure out who the thief is? Surely you must have seen this problem, right? In some variant form or even this form. These coins and so on, these are the recreational puzzles that we do, right? So here's the clever guy who's going to catch the thief. So what's he going to do? Yeah?
Is it the worst case or you want the average? I mean, you want minimum?
For my setup, it should be worst case, yeah. In this problem, 5. Not 1.
Not one?
No, yeah.
Can you take 1 from the first one, 2 from the second?
But that'll be, but he also needs to know how much, he needs to know how much is missing. He needs to know 2 questions, right? How much did he steal and who stole? They're both, I need 2 questions, not 1. I just don't want to know who the thief
But
is.
he knows that if he gets 1 and 2 and 3 and 4,
But he doesn't
he
know,
knows the final way
yeah.
that it should be.
He doesn't know if, yeah.
Then he also, but it depends on the.
Yeah,
there's
you-
one, at least on one.
What sort of balance you have? The two-sided or is it
No, it's whatever balance you want. He's got weights. Yeah. 2. Exactly. 2 is the answer. And why 2? Well, first measurement is he's going to take 1 from each. So he knows what is the amount stolen, right? The amount stolen will be what is missing when he does this total weight. So let's keep the reference, and this will be, say, -5. Let's say in the example, let's say 5 grams it's off by 5 grams. So we know that the thief stole 5 grams from each coin. Now, your point, how do I know who the thief is? I take 1 from 1, 2 from, among many schemes, you could do this. 1 from 1, 2 from the second, 3 from the third, 4 and 5, right? And then let's say when he does that, it comes out to be 20 grams short. So who's the thief? Yeah, so you have 2 measurements, y1 and y2. I divide y2 by y1, and I get 4, so 4 is the thief. So this is a general concept for many of the problems I'm going to describe later, okay? So keep remembering this. You can't forget it because it's just a cartoon, right? Cartoons you remember. Technical stuff you don't, which I don't blame you. I don't either. So 2 are enough. Now, so the key, the ratio test identifies the location of the thief. Now this location is going to be not a thief, but other things in what's coming. But you understand what's going on. So now I make it a little more, yeah, question. Yeah, I'm going there.
Suppose that for that example, you didn't have, each of them had less than 5 points. How can you achieve
You assume infinite. This guy's a rich guy, right? Yeah, you have an infinite supply of coins.
that? Number is important, right? And if it was a very small number.
Yeah. There are some technicalities you need to, but you understand the concept, yeah. Okay, so now I'm going to make the problem a little more complicated. You have 4 thieves among these 12 treasurers, and you want to find them. I won't engage you with what is the minimum number in the worst case. But if you want, you can answer that. But we can do it many ways, but here's one way. Okay. So here are so these are the 4 thieves among the 12 treasurers. And the key idea is I'm going to randomly group the treasurers. For example, that's one grouping. We'll call them bins. This is another, and another. So 4 bins. Okay. Now, I'm going to call a multi-ton if there is more than one thief in the group. Okay. I'm going to call singleton if there's exactly one thief in the group. And I'm going to call zero-ton if there's none, if there is any. Okay, so if there is a single thief, then I can do the ratio test as per the previous slide and iterate, because now I know the thief and how much he stole. So basically, the bad guy becomes the good guy for the next round. Okay, this is the key. So that guy is caught, and then that becomes a singleton, that bin, and so you can solve for that, and that will make this guy a singleton, and then finally that's a singleton. So I nailed all of them. Was I just lucky because I chose the example that way? Yeah, I was. I did choose it. But question is, how many groups are needed? How do you form these groups? And how do you identify if a group has a single thief? Right? These are all questions that we want to answer. And you could also use more complicated schemes like Reed-Solomon codes. You could take 8 of them and you have to solve systems of equations which will not be numerically stable when you deal with real numbers. So that's one of the, so we want to avoid both complexity and stability. So we want to keep it simple. We want to do simple peeling. This is called peeling. This is the basis for LDPC type codes. But the peeling is much more general. So in fact, the rest of the talk is all about peeling for many things. Okay? So the main result, which bases on the thief example, is that any band limited signal x of t. Now I'm going to switch to complex valued because I don't want to keep track of real stuff. So if you're complex valued and you have spectrum occupancy of f occupancy, it can be sampled at twice f occupancy by something known as a sparse graph coded filter bank. And it will approach one using, this is the key, the number of operations is only proportional to the frequency occupied. Okay? So remarks, the computational cost is independent of the bandwidth. So this is theoretically very interesting. So if you have 1 megahertz in a 10 gigahertz, your amount of computation is only proportional to 1 megahertz, not the 10 gigahertz. And it requires some mild assumptions of genericity, which, and again, I'm making some assumptions which are, I think, natural, and in some cases, it's not worst case. So worst caseism will get you, very hard problems. But if you relax some of them, you suddenly get good results. And it can be made robust with sampling noise, but I'm not going to discuss that here. Okay, so the key insight, remember we said that aliasing is a bad thing, right? So if you subsample, you get aliasing, but it turns out that if you subsample strategically, it's not a bad thing, because aliasing is structured noise. It's not random noise. And therefore, you can exploit the structure and aliasing to do some good. And in particular, filter banks derived from, say, what I'll call irregular LDPC codes. I'll go through that in a bit. From capacity achieving codes for the BEC can inspire how you do the sampling for this problem. You'd see, wow, what's the BEC that we talked about and capacity achieving codes for that play a role in sampling in this problem, which is kind of pretty cool. And the key is that we are not going to do linear interpolation as per Shannon's theorem or Nyquist's theorem. It's going to be highly nonlinear in the recovery, and that's the key. Okay, so let's walk through how we do this. This is filter bank for sampling. Again, we're going to break the band. This is my 10 gigahertz or whatever band into the FM is the maximum band that I'm considering. I'm going to chop it up into n channels. Okay, so each little slot is FM over n. Okay, I'm going to sample the signal at rate B. B is the number of bands. In which case, you'll have aliasing. All these things will collide on top of each other. Well, we know we can filter and then subsample. So imagine that I were to put a filter before I subsampled. If I filtered on the first slot, I get nothing. On the second slot, I caught the red. The fifth slot, I got the blue, and so on. But you can walk your filter through one by one and sample at B samples per second, and you will isolate all the frequency bands. So there are some arguments about how small I want to make. These are all limiting arguments, so don't worry about that. You assume n is large enough that things are in. It could be partial. For example, this guy is even partially in a band, but those are details. But I've not done anything useful in this because I basically sampled at the Nyquist rate. Because I need to have n of these channels, one walking through every one of these bands, and each one spits out a color, and of course, I will recover. I just put them together. But this is just the Nyquist rate. This is a definition of the Nyquist rate. So what do we need if you want to go below Nyquist? This is a square matrix, right? N by n. I need to compress. What do I mean? I need to have n bands in m channels or filters. I can only have m filters. I can't have n. If I had n filters, that's easy. I have only m of them now. Okay, so what does that mean? In this example, m is smaller than n, so it's a short, fat structure. And I still sample at B samples per second. Some of the bands, for example, this one is going to capture some aliasing of these two. This one will be lucky. He didn't get any. These two have nothing in them. This has a little bit of aliasing, and this one is also empty. It's also safe. So you can see here that if I marked a 0-1 pattern, whether I pass that band or filter it, if I pass it or stop it, you will have this 0-1 pattern, right? This is don't pass, don't pass, don't pass, 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 don't pass, pass. So I have a pattern. Now, that becomes a matrix. So this is like a parity check matrix in channel coding. Okay? So you see that you have n bands and m channels, and there's an m by n matrix, and you want to know how to pass these bands, where to put the ones and zeros, such that with high probability you will recover. Okay, so example. So these are the bands, there are 10 of them, and these are the channels, there are 6 of them. Remember, 6 has to be less than 10. M cannot be equal to n, otherwise you're not fooling anyone. Okay, so I'm going to populate that with, say I use this pattern to populate the filtering pattern. So you see that the first guy is 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. So basically he's going into the band C and F, just randomly. Likewise, I throw random darts from the left and let them land where they may on the right. I'm going to use that. So that's the scheme. Okay? For example, here's the idea. So I'm going to clean out all the bands that have no occupancy in them because they just clutter. So let's remove it for visual purposes. So this is my finished story. So measurement classification reminds you of zeroton, singleton, multiton. Reminds you of what? The thief problem. The same problem. You use the same principles. So what do? So you have, so in this example here, this is the pattern. You know that this has nobody in there. It's called a zeroton. These are singletons. They have no aliasing, luckily. And these have aliasing. So they're multitons. So let's set aside for now that I will find out how I'm going to figure out whether something is a singleton or not. There's a way to detect whether some guy has singleton or not singleton. Okay? So let's assume that. If you do that, then this becomes a matter of just peeling, right? Because the mechanism is, you know that B is red and F is blue, and these are single occupancies. So I can peel the channels from where they alias. So I know that this is a red, it also goes to D. So I peel the B and subtract it from the D. Likewise, I did that for the red, for the blue. Now that induces new singletons, just like we saw earlier. and that is going to peel the channels in the alias from. So it's just peeling. Exactly like we recovered those thieves from when you had 4 thieves, how I recovered all of them. Now, what is the mechanism for realizing? Remember, I had the weights, right? I had 1, 2, 3, 4, 5. What is the equivalent of that? Well, you just have to give some uniqueness to each band. How do you do that? Well, you give each of them a unique phase. Okay, it's a phase staircase of phase, and if you have a genericity assumption, which is not going to work in the worst case, but it will work almost always, then you can uniquely identify where the singleton is. It's kind of like knowing 1 from 1, 2 from the other, because they all have a unique phase associated with each band. Okay, so this is the principle, and what I'm going to do next is actually delve into how I design the filters, but which is essentially a tutorial on how you design low density codes. But okay, shall we resume? Yeah, there were. I just wanted to clarify. There were a couple of questions during the break on where the 2 factor is coming from on the filtering problem. So it's right here. So the first measurement is taken with magnitude 1 and phase 0. Okay, this is measurement 1. This is to if you want to map it to the gold thief problem, it's the all ones measurement. Okay, it's the equivalent of that. The second measurement is the weighted one. Its magnitude is 1, but the phase is unique. And the assumption is that you can identify from looking at just the phase whether it was a singleton or not, which assumes some genericity that if you have 2 bands that are colliding, the magnitude plus phase plus magnitude phase will not look like a single magnitude with that phase. Okay, there's a little bit of a assumption there, but that's almost always true. Okay, so that's why you're not in the worst case, but you're good enough. That's where it works. Okay, so I'm going to run through very quickly construction of the sparse graph code. Remember, I told you have to make those 1s and 0s in a particular way. I'm presuming that some of you have not seen sparse graph code design, so this is a school, so let's do a little tutorial. So we'll derive some of these equations, but very mildly. Okay, so as I said, you have bands on the left, channels on the right. Channels is less than bands because you're compressing. And you want to connect each band to the channel according to a carefully chosen randomness. Okay, what is that randomness? So it turns out if you choose it properly, asymptotically, the number of channels that you will use is only a tiny bit more than the number of active bands. Okay, you can't do less than the number of active bands, then you lose information. But 1 plus epsilon, where epsilon is arbitrarily small, this is theory. And the degree distribution turns out to be this. Okay? And for those who have seen the soliton distribution, or in terms of this is the probability that the degree is j is proportional to 1 over j times j minus 1. And this is, if you want to visualize it, this is how the distribution looks. For an epsilon of 1 over 20, where it's a truncation factor. So epsilon is the leeway you get for being away from capacity. And in this example, d will be 22 because whatever. That's what the epsilon was chosen. And otherwise, you have a decay. And this is known as the sort of soliton distribution. And this was done by Luby et al. But the connection is interesting. OK, so the connection is that bands map to variable nodes and channels map to checked nodes. Okay, this is coding theory language, random codes. And I'm not going to do the irregular degree, which is complicated. I'm going to simplify it and make it regular. That means all the bands are going to randomly choose, let's say, 3 channels on the right. Okay? Everybody shoots 3 arrows from the left. Wherever they land, and you do your analysis. So we'll first show that analysis, and then we'll leave it to you to do the more complicated one. Okay? It's not that different. Okay, so let's go through that. So the regular graph construction is every variable node on the left throws 3 arrows, and to d arrows in general. And so there's a technique called density evolution in analyzing how these graphs, ensembles of graphs work, which we will walk through. So these are the active bands on the left. So these are the bands that have energy in them, and these are the channels, right? So the number of active bands is much less than the total number of bands, right? That's why we are exploiting that sparsity. But the number of channels has to be of order k, of order active bands. For example, for d equal to 4, the way you do this technique is that you draw an edge from the check node to the variable node, represented like this, and you pick an arbitrary edge, and you examine its directed neighborhood at depth 2L, which means you build a tree-like structure, and you find what is the probability of having what is the directed neighborhood story of depth 2L. So let's assume that PL is the probability of an edge being present. If an edge is present, that means it's not been peeled off, right? Which is a bad thing. So presence of an edge is a bad thing. You don't want edges. You want everything cleaned out. So PL is probability of being present at depth L, 2L. And so PL minus 1 is the probability of the previous. So basically what you're doing is you're unfolding this graph, and you're going from left to right and following the leads, and you're just plunking them in this tree-like fashion. Okay? So that's called unfolding of the graph. So how do you analyze this? We'll do an average analysis. First, we're going to assume it's a tree. That means there's no cycles. So assume it's a tree. That means there were no cycles in this graph. So in this example here, this was the red, and these are the 3 blues, and then you chase these down, and you go to some depth, a finite depth, and you'll see it's a tree structure. Okay? With high probability, you will show that it's a tree. I'm not going to go through it, but you assume it's a tree, and you analyze what is the probability that that edge still remains at iteration L, at iteration L minus 1, so all the way up to iteration 1. Okay? So this is the trees of depth 2L. 2L because this is 1 and this is 2. Okay? Because C to V and V to C is one round, and another C to V, V to C, so there are 2 of them. Okay, a check node is resolved. So key, when will a variable node V be resolved? Well, if any of these check nodes can bail it out, then it's good to go, right? Because all those check nodes are telling you, I know your value, because there was a singleton there. Now, a check node is resolved only if all of the children nodes below it, variable nodes, are resolved. So there's a any and all distinction between these. So how do I do, for example, if this variable node had 3 check nodes, so right to left, then what is the probability that of this event? What is the probability that this thing is not resolved? Well, 1 minus PL minus 1 is the probability that it is resolved, and it happens to have 3 children, so it's cubed. And 1 minus that is the probability it's not resolved. So this is the way you do the calculation. This is for just this check node. Likewise, you do it for that one, which happens to have 2 children, and this one happens to have 2 children too. So the probability that this is not resolved has to be the product of all of these. Okay? Now, where do I get this 3, 2, and 2? They are the number of children of the check nodes that have, it turns out, when you throw regularly or irregularly from the left, on the right-hand side, you have a binomial distribution, which in the limit becomes Poisson. Okay? And the Poisson degree is kd over m. Why? Because you're throwing k times d edges from the left, and they have to land on m edges, m nodes on the right. So the average has to be kd over m. That's the average rate of the Poisson process. Okay? Anyway, so it turns out that you can calculate the probability that a check node is resolved using the Poisson distribution for estimating the number of children that we have marked in blue here. That's the C. And when you work it out, it's very simple this converges to e to the kd over m PL minus 1. Okay, so this is just the math. So more generally, when you take 1 minus that, it will become, because you have a 1 minus here, this is the probability that it's resolved, this is the probability it's not resolved. It becomes 1 minus e to the minus kd over m to the d minus 1. So this is it. This is the whole density evolution equation that characterizes how this graph will behave. So the key point to note is that we want PL to go to 0, right? You start off with PL, P0 equal to 1, and then you want to keep going lower and lower and lower until you're vanished. So we want, in particular, you want this to be a contraction. PL minus 1 should be, PL should be less than PL minus 1. And basically, that will happen if you, remember, you have control over K, D, and M. These are your parameters, your tuning parameters. If you choose them properly, PL will indeed go to 0. Okay, so this is the key. Okay, this is done in terms of a so-called exit chart in density evolution. And again, recall that K is the number of active bands, M is the number of channels, and D is the left degree, right? So this is the equation. If you plot this equation, you will get something like this blue line here. The red line is a 45-degree line. You must stay below the line, because if you're above the line, that means one of the PL minus 1s is greater than the PL. That's no good. So you have to stay below, and the amount by which you stay below tells you how much off you are from capacity. So this is called the area theorem. Okay? Anyway, these are details. So you start off with P0 equals 1. So the exit charts were introduced by Ten Brink in 99, and they are detailed in Richardson and Urbanke's coding theory textbook. Okay? So this is the reference for this. So P0 is 1 because at the beginning, all my edges are still around. And then P1, you just follow that equation. It goes down to that. So you follow the staircase, and you see that at every iteration, P is getting smaller and smaller and smaller. And this, the area under that tells you what you will get. Now, that's what we did when D was fixed. That means from the left, you're throwing exactly D arrows. But it turns out that if you are careful about how the regularity or the irregularity with which you throw these degrees, you draw it from a distribution, then you can make this thing get much closer to the red line from the left, which means you're very close to capacity. Okay? So this is the theory. So the density evolution, it turns out, you can check for yourself that the degree distribution, irregular degree distribution that I had mentioned earlier, if you plug it into the formula here, you will see that indeed PL goes to 0. And not only that, the blue curve stays just below the red line. And how close it is to the red line is how far away from capacity it is. So this has to be carefully chosen. I won't talk about how you do it. It's already done, so we don't have to worry. So this is already done. And if you look at the density evolution pattern, it starts, and then there's barely any space between the red and the blue lines. Okay, now that's the average analysis. To complete it, you have to complete the story. I'm not going to bore you, but I'll at least mention the highlights. So density evolution assumes that the tree is a tree, and the tree-based is an average analysis. And you can show that L can be done in a constant number of iterations. You can get PL to as close to 0 as you like, but not exactly 0, as close to 0. Okay. So you have removed KD. KD is the number of edges times 1 minus PL. What do you do? How do you show in practice? Well, there's a concentration argument you have to use. Okay? Basically, you need a Doob-Martingale type argument, and you can show that the average behavior is the actual behavior with high probability. Okay? There's some details, probability details. So the actual number of the probability that you have more edges remaining than KDPL is arbitrarily small. But you're not done, because this is the number of edges that you have removed. You still have this many edges remaining. Who's going to take care of those? Well, it turns out, in addition to that, you need an expander graph argument. So just to show you there's some technicality here. Yeah, question? Oh, no. You can show rigorously that the probability that you are not a tree vanishes as n grows. The number of bands. No, nothing has to grow. Number of edges is finite. Yeah. I mean, what you can show that the reason is that you can show that in a finite number of iterations, you're done. Okay, that's the key. The key is you're not waiting forever. You're done in 4 iterations or 10 iterations. Okay, so, and the final piece of the puzzle is that you have an expander graph argument. It turns out that if you throw regular from the left or irregular from the left, you have so-called expansion property of the graph, which guarantees that if you have removed this many edges, if only this many edges remain, the rest are going to completely go through. So that's what expansion means. I'm not going to elaborate on the details, but instead I'll show you how a numerical experiment on the sampling and filtering problem works. So you have this input spectrum here. It has, I think, about 10% occupancy. The measure is 0.1. The number of slices is 1,000. And the number of channels, M, is 284. Okay? So much smaller than 1,000, right? Sub-Nyquist. And in particular, the sampling rate is 0.284. Well, if it had been ideal, the number of channels should have been a little over 100. But for these small numbers, this is what you get. Okay? So it's a little more than 100, but much smaller than 1,000. These are the outputs from 2 sample channels. And this is a zooming in of so this is the frequency spectrum, and this is the actual time domain. And if you zoom in here, you get these, you see that the true signal estimates the true signal is in red, and the estimates are in blue. Of course, this is a noiseless setting. But this is to show that it's a constructive scheme. It's not just some theory. Okay, so that puts the end on that, but I do want to end by saying that this project reveals a very interesting and, to me, unexplored connection, fundamental connection, theoretical connection, between sampling theory, which we all know from DSP, and coding theory, which we know if we study LDPC codes and beyond. These two are linked intricately, and I don't think this was known before. Because of this project, we were able to discern the connections. So minimum rate spectrum blind sampling is intimately connected to coding theory, and capacity etching code for erasure channels map to these random filter bank structures that we designed, which approach the Landau rate. Okay, so time to take a step back and understand the big picture of what we did. Okay? The key was we did all this density evolution stuff with graphs and so on. So I call that a peeling-based turbo engine. That's all we did, right? We just peeled bands from each other. Now this is feasible in practice because when you're peeling a band, all you're doing in the time domain is you're subtracting. The time domain samples correspond to the frequency domain spectra that you have. So when you're stripping it, it just means subtract these samples. Okay? So it's feasible. So peeling-based turbo engine is the sort of heart of what makes everything work. And this is powered by a sparse graph code. So sparse graph codes are very powerful. That's the codes that we just talked about. And what they do is there are many kind of children that help this turbo engine to run. What are these engines? These are solve if trivial sub-engine. These are the singleton detectors. So if you have a singleton, please peel it and please give me back what you have, because I will help the other children with that. So that's the philosophy. Okay? The big picture is this is a key diagram, and you'll see, and these guys are saying, I concur that this is a singleton and give back. So it's a concur and divide, if you will. Okay. Now, it turns out you can use this philosophy for a host of applications. I mean, you can't even name how many you have. This was just done for the sampling part. That's what we did, sub-Nyquist sampling. But this philosophy can be used, in particular, you can have a discrete version of this which has applications to MRI, which is the DFT and also the Walsh-Hadamard transform, which has applications to graph sketching. So these are things that fall out of this. Other things are you can use this for doing group testing, and that's useful, for example, in fast neighbor discovery. I talked to many of you who work on group coding problems, group testing problems, and there may be other applications. Of course, compressed sensing smells like this should belong here, and it does. Okay? So compressed sensing can also be used using this philosophy. Then there is also sparse mixed linear regression for learning. So if you have parameters that are sparse mixtures of linear regressors, you can learn the parameters of the estimation using this scheme. And finally, there's also a compressive phase retrieval, which is used in optics, where if you don't know the phase of the signal, you can use. So the key is that you have to be creative in how you do the singleton detector. That will change on a problem-dependent way, and oftentimes you have to get really out-of-the-box thinking on those. For example, in the compressive phase retrieval, singletons don't help. Okay? Singletons were the key to peeling, right? But they don't help. But doubletons help. So there's all kinds of nuances to that. So I'm going to walk you through the sparse spectrum because that's where we actually have some practical results. And so I'll go fast through this because we saw related work in the sampling case, but let me walk through it rather fast. How much time do I have, Bobak? It's 3:30 now?
Yeah, 3:30, so.
Okay. We might take a break before.
Well, then including questions.
Okay, yeah, sure, yeah, of course, yeah. Definitely, that's most important. Okay, so let me tell you how to speed up learning. This is chapter 4. And sparse recovery. Okay, of course, this is an age-old problem. And Samir, Simon, and Orhan were the co-authors on some of these works. Okay, motivation. Okay, you never need to motivate here, but you're given training data points, x, y. Our goal is x might be the features, y may be the labels. It's the data set. You want a certain rule. After all, that's what all the deep nets do, right? Neural nets are trying to figure out what's the function that explains y equals f of x. So for example, if x is area or bedrooms, these are your features, y might be the house prices, and the questions of interest is how many data points do we need, how long does it take to compute, right? These are the burning questions. And robustness, how accurate and stable is this? These are the typical problems we face in learning theory. Well, we're going to dumb it down a bit, and we're going to assume things are polynomial just to get the thing going. So let's say that you know that f is a linear polynomial in two features, x1 and x2. And the problem dimension is 3. That's an easy problem, right? You all know how to do it. However, in reality, it's this, right? I don't even know what I wrote, but it's some junk. It's a very complicated thing, but we don't know what it is. And the problem dimension also is going to infinity because the number of features is getting large. So what I want as an idealized, as a wish list is problem dimension is n, and if you have something that is polynomial in n, which is sample cost and runtime, whatever, then you basically are, as n increases, it's going super linearly. So, well, that's hard. So what if we can actively choose training data? So you cherry pick which data points you want, and the model intrinsically has sublinear degrees of freedom. You have to have something going for you, right? You can't have n going to infinity and the structure also going to infinity. I mean, at a lower rate than n. So you want to, you aim for doing a sublinear time algorithm, which just means that as n increases, the time it takes for you to recover or do your job or infer must go sublinearly in n. Okay? So this is a wish list. And the question is, can we achieve this for fast and robust learning with active sampling? By active, I don't mean the way Tara meant it. I mean like as a membership query. I'll tell you in a minute. And coding theory. So this is a one-time thing. You have to decide what to do. Adaptive things will do even better. So maybe some of what Tara talked about could be added on top. Applications are plenty. So there is MRI, there is machine learning, IoT, computational imaging. There are many, many applications for the spectral part that I'm going to talk about. Okay, so I'm going to talk about sparse spectrum. So let's start with polynomial learning, one of the easier problems. So we know that if I have an nth degree polynomial, or n minus 1th degree polynomial, how many points do I need to recover the polynomial? I need n points, right? You know that if I have a quadratic, I need 3. If I have a 7th degree, I need 8, and so on. So how do we do this? Well, very simply, I write down a system of equations. So I know that, so the model is that you input with an xi and out pops f of xi. So it's a black box model, right? So you feed it an xi and outputs f of xi, and because of the polynomial nature, you can see that you have this system of equations. So you want to solve for the capital F's are the unknowns, because those are the coefficients, but you have evaluations at little f, and from that you solve. Well, how is it related to the Fourier transform? Very simply, if you choose the complex roots of unity as your query points, you exactly get a Fourier transform relationship, FFT, IFFT. This is your DSP 101, right? So as long as you make these xi's e to the xm's e to the I 2 pi over nm, where n is the number of samples, or the degree of the polynomial, you will get exactly this relation. But the problem I'm interested in, which is what we're going towards, I may have a huge degree polynomial, say 1,000,000 long, but my sparsity is only 200. So I don't know which 200 of those polynomial coefficients are significant, and I want to find them. So this is a learning problem. And how do I do that? And k is much, much less than n. In fact, k over n will go to 0 as n gets large. K may get large, but as a ratio, it will go to 0. So this is the setup. So question, how, for example, if the sparsity was 200 in 1,000,000 lengths degree, how many samples and what cost do you need? Well, spoiler alert, I'll show you a scheme which requires 616 samples, and the computational cost is independent of n. It's order k log k. It's pretty amazing. There's no dependency on n. N could be 1 billion, but it won't affect this answer. So it's kind of, I mean, there are constraints, okay? I don't want to say this is the best thing ever or anything, but there are constraints and there are some assumptions under which this will be true. But still, it's remarkable that it works. So let me walk you through that. So the discrete Fourier transform of a signal x, which is, we're going to assume complex valued. We know that the computational cost of the FFT is, by now you know, n log n, right? So n log n is how much time I need to spend. If only k out of n Fourier coefficients, it's the same. It's the same problem. So solving this is the same as solving the polynomial problem. Okay, it's the same. Okay, problem formulation and results. I'm just going to give you some of the assumptions. So I need to solve for the significant coefficients x, capital Xk, given the time domain, where I'm going to assume that the sparsity is uniformly spread at random. Okay, so it's not worst case. Okay, you must be uniformly spread. That's what we can prove. We came up with this fast algorithm, which was recently accepted last year. In the noiseless setting, for k sublinear in n, it uses fewer than 4k samples. This is when the k is a sublinear in n. Say k is n to the delta, and delta is between 0 and 1. And this fewer than 4k means delta can be as large as 0.999. Okay, I mean, it's almost the whole space. You can't go all the way, but and it's order k log k computation, and it's also robust to noise to some extent. I wouldn't say it's perfectly robust, but it is robust to noise, and you'll need a log n factor. It turns out some strange 4/3 and 7/3. Don't worry about that. So you can think of it as some log or log squared. But it's still sublinear in n, right? That's the goal. The goal is to be less than n. And log n, k log n, k is less than sublinear in n, and log n is certainly sublinear in n. So that's the goal. So again, I'll very quickly walk through this because you've already seen this before. So when you sample, you get this. When you subsample, you get that. And if you sample below the Nyquist rate, you get aliasing. But if you're smart, you can get good alias codes. The key new ingredient I want to introduce here is the use of the Chinese remainder theorem in the subsampling patterns. And when you do that in a careful way, you get sparse graph codes coming out. Just pops out. Okay. And therefore, since sparse graph codes come out, we are set because we have our toolkit. We've already looked at that. We just go and, with slight modifications, we can use those tools to analyze everything happening here. So we'll give an example. I like examples. So imagine that you have a time domain signal of length 20, and in the frequency domain, there are exactly 5 non-zero coefficients at those positions, 1, 3, 5, 10, and 12. Of course, the algorithm doesn't know it. but the length is 20. So I'm going to subsample by 5. This is the crux of how this works. If I subsample by 5, what will happen? Well, you know that I will then, after I subsample by 5, I will have 4 samples. I will take its DFT of length 4, 4-point DFT, and what will your measurements look like, and how are they related to the DFT of the 20-point signal? Again, this is DSP 101. You'll see that you will have aliasing, right? And how do you alias? You take every 4th sample and mix it here, and so on, right? So 0, so this is exactly how the aliasing pattern behaves. Now, so 0, 4, 8, 12, and 16 added up into bin 0, 1, 5, 9, and so on to bin 1, and so on, right? This is a relationship between time and frequency. Now, what you do, remember, I need an analogy of the thief problem where I had 1s, and then the second measurement was 1, 2, 3, 4, 5, right? I need something to distinguish because I need to find singletons. That's where I'm telling you where I'm headed. So how do I do that? Well, I shift and subsample. Wait, I went too far. I subsample, okay, I'm sorry. I got ahead of myself. When I subsample by 5, I have aliasing. But the hope is that many of these aliased patterns don't matter because they have zeros on the top. So for example, here, you see that U of 0 had nobody, U of 1 had 3 people, U of 2 had 1, and U of 3 had 1, right? This is the singleton pattern. So this is a multiton and singleton. Now I'm going to, this is the second measurement, I'm going to shift and subsample. If I shift in the time domain, what happens in the Fourier domain? Phase offset, yeah. And it's a unique phase that identifies the location of how much you shifted by, right? Of the frequency. So in particular, you have omega to the 1, x of 1, omega to the 3, 5. In fact, the amount that you shift is a function of the location, which is what I'm after. So again, going back to the thief problem, it's a dead giveaway who the thief is, right? So that's what we need. So you do this, and we're going to write it from the right now. Bear with me. So I go from right to left. I subsample and take a short DFT, and I get that. In fact, most of the complexity is in taking the short DFT, okay? But it's only order k, so that's why it's k log k. Okay, so then I shift. This is my second measurement. I need 2 measurements to identify singletons. And that's what I did. And why not sample by 4? I sampled by 5, subsample by 5, my length was 20. Let's take the other factor, 4, and do the same. And you can build this graph of aliasing patterns. And in particular, and you can keep going on this. And then as the story is clear, you'll just hope that you can peel it away. So how do you do that? Again, you identify a singleton, which is at x10, and then you strip it and create more singletons, peel, peel, peel away. Happy peeling. So sparse DFT computation is exactly decoding over sparse graphs. Same problem. Okay. Does it always work? No. Why should it? I just gave you this example. How do you induce good graphs that will be guaranteed to work with high probability? Right? So the sparse DFT computation, just as an analogy to communications problems, it's a sting on the, you want to identify these non-zero coefficients, and these are the aliased frequency bins on the right. There's a good analog to erasure channels, erased packets. So when you get a packet that's erased, you get all these erasure patterns, and we have parity check codes that we know how to design to correct these erasures, right, to replace them. That's what coding theory does. But there are some differences. In this case, you explicitly design, but in this case, it's implicit because this graph is induced by subsampling in the time domain. This is a frequency domain picture. I cannot induce any old graph in the frequency domain. We have to subsample and then hope that whatever comes out will be good to go. Okay, so that's what we're doing here. And Of course, there's an obvious analogy between the number of received packets and the number of non-zero coefficients, number of erased packets. And the other thing is in the erasure channel, the channel tells you which packets are erased. But in this problem, you don't know the locations. So you have to pay twice the price. Okay? That's the high-level picture. Okay, so the other thing I want to point out, where does the CRT come in? I mentioned the Chinese remainder theorem, CRT stands for. Well, you have, when you go back to balls and bins, which is the sparse graph codes, that's how you analyze them. Let's say you throw degree 2, 1 in each stage. We call these stages. So whether you throw 2 to one stage or 1 to each of 2 stages, it's the same asymptotically. So basically, let's say that every ball is thrown randomly into one bin on the top and one bin in the bottom. Okay? So that's the model. So this is what I throw. And this is the pruned graph. Okay? These are the balls that are to be recovered. They are erased balls. On the right, the Chinese remainder theorem induced graph is for our problem. Okay? What am I doing? I'm subsampling by 4 and by 5, right? So when I subsample by 5, I get 4 bins. When I subsample by 4, I get 5 bins. Okay? And I'm doing mod operations when I do binning, right? So what do I do in particular? So this coefficient, this ball goes to 2 in this bin and 0 in that bin. What does the Chinese remainder theorem say? Well, if I know that the number of balls, total number of balls was less than 20, then this ball is a unique label. There's only one number which can be 2 mod 4 and 0 mod 5, and it's less than 20, right? Between 1 and 20, 0 and 20, 19. And that's what we use. So in particular, you can work it out. That's number 10. The ball 10 will have 2 in mod 4 and 0 in mod 5, and no other ball. So it's a unique label. So when you do the analysis, it's very clear that anything that this guy can do on the right, this guy can do on the left, because this is the ensemble of all random graphs. Right? That's what the analysis is based on. What's less clear, which is what the CRT brings, is that anything that the left guy can do, the right guy can do also. So it's a direct equivalence. Because any ball that was thrown here has a unique label 10, so that must have been ball 10. We didn't care about that in that problem, but it turns out, in this example, you can label these balls, give them numbers, 1, 5, 10, 13, and 3. They are the ones that have this edge structure. It must be the same on the left. And so these two graph ensembles are identical. So to analyze this, you can just analyze the left-hand side, which is easy to do. Okay? So that's how the two problems are related. So you can use, in particular, LDPC codes and density, all the stuff we've talked about. Okay. Now, back to the sort of the problem that I had given you. Remember, I told you n was 1,000,000. In particular, it turns out these have to be prime factors. Doesn't work for any old n. So 100, 103, and 107 are roughly 1,000,000 when you multiply them together, right? A little more. And k was about a 200 is what I said. And you'll see that m is about 600. And how it happens is you subsample by the other factors, so 100 by 103, and then you take a short DFT, 107 length. Then you subsample by 100 by 107, and you take 100. So you do all 3 patterns. And the number of samples you get is roughly 600, right? Because each of these spits out about 100. There's 6 of them. 2 per, because you need to identify the singletons. And in particular, that's how we get the 600 number. Okay, so this is kind of showing that the theory is working in practice. So the theoretical threshold is 1.23. So remember that number. It came from our density evolution equation back when we did it last time, earlier. So you'll see that, and in particular, here's my exit chart for this. If you, this is the density evolution equation for degree 3 on the left, and the fraction of non-zero. So this is the probability that you recover, you're not recovered at t plus 1, and this is the probability you're not recovered at t. And this graph, if you stay above the blue line, a black line, you're not doing well. That means it's no good. But if you stay below the blue line, you are. It turns out that d equal to 3 is the optimal thing in terms of staying just below the line. And it gives you a 1.23 hit from capacity. And that's a 23%. And here is kind of the practical scheme, where n is about 8,000,000, k is 400, and m is about 1248 samples it almost jets right on top of the theory line. Okay, I'll just give a word on noisy to noiseless to noisy. So remember, we had many stages depending on how many factors we had in our factorization, but each stage consisted of a subsampler and a subsampler with a shift, right? That was the mechanism. What we need to do when you have noisy case is that we need to invest a lot more of these shifts. Okay, you can't just do. You have to do noise averaging on the weight. So it's kind of like if in the thief problem, if you had some noise in your measurements, what would you do? I take more of them and average, right? That philosophy goes through for the most part. Okay, I don't want to dwell too much more, but if you use more shifts and do some other tricks, it will work. Now, I want to talk about the applications of this. This is what excites me the most, to an important application of MRI, magnetic resonance imaging. So this is where when you're imaging the human body, you are getting samples in the Fourier space. It's called the K space. And you want to invert that to find the image. So you really want to find the image, but you'll get access to the Fourier samples, almost tailor-made for our setup. But you need to have sparsity. So for the most part, you can find sparsity in real images, either spatially or in some other domain which can be handled. But more importantly, in the temporal domain for dynamics. That's more important. So here is a kind of a cartoon demo of a numerical phantom for cardiovascular MR. This is taken from Zurich. And in this picture example, the size is 336 by 323. Note that they are all prime factors, so it's chosen carefully. And this is your beating heart, and these are temporal differences across different frames of the phantom of this cartoon imaging. And you see that it's very sparse. If you take successive differences, they're very sparse. And so you hope that they would be amenable. In this example, we took about 1/3 of the Nyquist rate. And this is a screenshot of a real-time MATLAB running. And, oh, it's not running. Don't know why. OK. Let me see if it ran. OK, never mind. So what I wanted to show you was this can reconstruct this in real time. Okay, so take my word for it. Yeah.
How does this compare to compressed sensing for MRI, or are you just designing this?
This is a compressed sensing scheme.
Instead of using
Yeah, we are using compressed sensing. You can't use any old matrix, right?
Yeah,
You have to be Fourier. You have to be Fourier based. So this, you can think of this as a compressed sensing for MRI. This is kind of in that spirit. Yeah. Anyway, so it's too bad I didn't have the. If you maybe offline I can show you, but if you click on this, you'll see that it samples it at 1/3 rate, and most important, it processes it in real time, because this is very fast. So the hope is that, and it reconstructed perfectly. It's a cartoon image, but we also have it for actual images. So I'm working with one of Mickey Lustig's students. Mickey is an MRI expert in Berkeley. Okay, so now I want to kind of dream about what we can do with this within reason. So who knows what that is? If you have already seen it, don't yell. What is that? What is that monstrosity there? That's a digital camera from Kodak in 1975. Of course, Kodak is RIP, right? They're gone. They went bankrupt. Too bad. If only they had stayed ahead of the times, they wouldn't be this way. They invented the digital camera, believe it or not. Okay, so that's a Kodak digital camera from 75. And the way they used to view the photograph is they would tether it to a huge television, black and white, of course. And of course, times have changed. Of course, even beyond even this picture is from 2000, so we're 20 years past that. And in particular, what we can dream of is to do a real-time MRI with a viewfinder. With this technology, you can actually, because you can do it in real time, you can give the radiologist a viewfinder that he can see everything, and then click on, and when you click the picture, you can do full compressed sensing processing, or because this thing is fast, but not as good in all conditions. But the fast part is what we want to capture. So this is something, if any of you wants to work on, would be great. I'm not doing it, but this is a good dream thing. Okay, very quickly, I want to tell you a related problem, which is a cousin of the DFT, which is the Walsh-Hadamard transform, and how it's used for recovery of pseudo-Boolean functions. There's an application there that's interesting. So now this is the endpoint DFT that we've just seen. Now the Walsh-Hadamard transform is it's a Boolean cousin of that, where you choose n to be 2. So n is always 2. So e to the I 2 pi over 2 is e to the I pi, which is minus 1 is minus 1. So, but you are choosing n to be, n is 2 to the n. The number of, you're doing a 2-dimensional DFT, but across multiple dimensions. And if you want to visualize it, it's like a high-dimensional DFT over the hypercube. So you're taking 2 points in every dimension and taking the transform, Fourier transform of that. That's exactly the WHT visually. And the application space is more because now this is tailor-made for machine learning, in the sense of many applications in machine learning will have sparsity in the Walsh-Hadamard domain, and things like decision trees, regression trees. There are applications to biology and hypergraph sketching, which is something I will get into in a bit. So just wanted to make sure that we understand the application space. See, we looked at polynomials in the Fourier case and related them to the Fourier transform. It's the same story for Boolean. It's no different. So this is the equation for the Walsh-Hadamard transform. So this is an inner product between k and m are binary indices, one in time, one in frequency. Okay, so that's what they mean. So you take the inner product of 2 binary vectors, raise minus 1 to that inner product, and multiply that by fk. Okay, so in our problem, f sub k is the Walsh transform, and the assumption is that f of k is sparse. Okay, and I'll show you examples where that's the case. So how do I get a polynomial representation? Very simply, you replace minus 1 to the mi by xi. So when you do that, I'll just give you examples to see how it goes. When n is 2, little n is log of big N. So you get n is 2, so you have 2 variables, and x1 and x2 are related in this way. So you note that you're getting all couplings of x1 and x2 up to degree 1. So you have x1 by itself, x2 by itself, and x1 and x2 together. And n is 3, you get 1, x1, x2, x1, x2. There's a power series for all the terms of the form of x1 to the I, x2 to the j, where I and j are just 0 or 1. Okay? So this is the expansion that relates the WHT to a this is a multinomial representation. So you can see here that there are 8 variables to be observed. And if you can probe, xi's are plus or minus 1. If I can probe the xi's at plus or minus 1, I need exactly 8 equations to get 8 unknowns, right? Just like we saw in the Fourier case. So this is a Fourier case. So for example, if you're in 4, you have to recover these guys. If I solve for this, this is the pattern that you get. This is the Walsh-Hadamard transform. Okay? So this is the connection. Now, if you want to recover f, so this is called a pseudo-Boolean function because this is Boolean, but it maps to a real valued number. So this is what pseudo-Boolean functions behave like, the mapping. So you put, this is like a truth table. You give an input of all ones, you get the output f. Then you change the last one to minus 1, you get another, and you enumerate all of them. There are 2 to the n of them. There's a complete truth table, right? You would get any function that you want. You get the function of these, and in general, if all of these f's are unknowns, then you need all of them to solve for the f's. So that will be a WHT. Now, again, just like in the previous case, suppose I told you that only 64 out of these 1 billion possible input combinations, when n is 30, you have 2 to the 30 possible things in the truth table, that's a billion. But I tell you only 64 of them are significant. And now this is useful, for example, in machine learning, when you have so many features, you have some influential features, right? There are not that many influential features. You may have of the order of 60 or 100 influential features, but they're not just linear. You have couplings. And this takes care of linear couplings between features. So it takes you to some extent. And it turns out that the number of evaluations is, again, this number 1.23, which you should know by now, times k times little n, which is sublinear in capital N, because little n is log of big N. Okay, so in this example, what is the result? The result is that you can learn the pseudo-Boolean functions whose spectrum is k-sparse with a sample complexity which is order n log k. N is log of big N, so it's a sublinear in N, with a computational complexity which is nk log k, and it can be made robust to noise. So the insights are the same as before. Okay? Subsampling is aliasing, but smart subsampling leads to good alias codes. But now you operate in the Boolean space. So very quickly, again, we saw that the equivalent to high-dimensional DFT, for those who know imaging, so this is the Boolean representation. This is a you're doing 2-point in 3 dimensions, and these are the Fourier coefficients. And if you were to keep only samples C0 and C1, shown on this face, it turns out that the aliasing pattern will involve the planes that are orthogonal to your sampling direction. So wherever you have a sampling direction, look at the orthogonal planes that intersect, hyperplanes that intersect. You have to add them all up. That's the aliased pattern that you get. This is an instance of the projection slice theorem in tomography, if you know that theorem. So again, if I sample C0 and C2, I will get the orthogonal guys, C2 and C5, the projections. Likewise, if I go vertically, the top and the bottom will alias. So this is the aliasing phenomenon in the WHT. So I'm going to apply this to a hypergraph sketching application, where I'll indulge you. It's a very old app, but N is the number of books. This might be Amazon. So people are purchasing books, and they want to know what patterns people are purchasing in. And S is the number of sales patterns in these books. For example, X1 and X2 may be purchased together. So you want to know that, because those who bought X1 also bought X2. And likewise for X22 and X23, or X9 and X14. So these are frequently bought books together. This is Twilight Saga example, don't worry about it. But these are books that represent a theme. And what I want to do, so hypergraphs are just graphs which are generalizations of graphs which have more than, their edges can be of sets of nodes. But we'll not worry about that. We'll just go to the edge case, to the graph case. It turns out that there are 2 to the n or 10 to the 9 possible hypergraphs for this problem. Even for n equal to 30, you'll have a billion. So it adds up in a minute. So what do I do? Well, the question is there a data structure whereby I can recover all these sales patterns, which are called the hyperedges? In this case, they're just edges. But if they had more nodes in them, they would be called a hyperedge, without logging every transaction. So I just want a summary of this. And it turns out a useful data structure is so-called cut function of the graph. Okay? So what it does is, I'll just explain it graphically. You put a cut through this graph. This is a graph, and it's a sparse graph because most patterns are not brought together, right? There are only a few that happen compared to all possible things. So I put a cut here, and I put everything on top to be +1, everything bottom to be -1. So in this example, how many cuts do I have for this graph? 0, because there's no cut. The cut didn't penetrate any edge, because edges were either on the top or on the bottom. Well, I could, if I use that cut function, or rather if I cut the graph that way, then again, I go ones here, -1s here. How many guys cross? Exactly 1, the green one, right? The green edge crosses it, and you log that. So you can keep doing this, and you'll get patterns. It turns out that this cut function is actually the multilinear polynomial that we discussed earlier. So in other words, you can look at the cut function and map it one-to-one to the graph that you want to recover. So in this example, forget the normalization of the 3/2, 1/2. They're done for maintaining some property. But you notice that the edge structure is evident in the polynomial, in the multinomial. For example, it contains the terms x1, x2, which is an edge, x9, x14, which is an edge, and x22, x23, which is an edge. So these edges are embedded in the cut function. So if I want to learn the graph, just learn the cut function, which is going to be sparse because we know that most of the edges are missing. And so it's a very convenient way in which you can cut down the number of samples, how much data I need to collect to learn a graph. So that's the application to WHT. So in particular, if the number of sales patterns is much smaller than n, and the number of items per sale, D, is much, much smaller than n. In this example, D is 2, because D is the number of edges, elements in an edge, a hyperedge. You get a k-sparse polynomial, you can show that a sufficient condition is k has to be smaller than or equal to s times 2 to the d minus 1. When d is 2, k is smaller than 2s. If s is 4, k is of the order of s rather than of the order of n. Okay, so what do? Subsample the cuts. You don't need all these cuts. In theory, you would need all the cuts if I want to discern the entire graph, but most of the edges are missing. So let's subsample the cut function liberally. So let's do it. And then you recover the hyperedges. So here's an example of how this works. On the left, I had 50 books, 2 items per sale, and 250 sale patterns. This is actually a sparse picture. You can see daylight inside, it's really sparse. If you had to draw every edge, you wouldn't see all black. Okay? This is actually a sparse graph. What do? Well, does it satisfy my conditions? The total number of cuts, if you were to do this, sample it, is 2 to the 50, astronomical number. The sparsity is about 500 if you use this. And it turns out, I'll show you an example where the number of cuts is orders of magnitude less than what you need. It'll be of 25,000, of the order of 25,000 for this. And what do? You use the subsampling tricks that we talked about, and you subsample based on strategically placed cut locations. And this is after one iteration. This is the iterations of the LDPC stuff. Okay? Second iteration, third iteration, fourth iteration, and you're done. Very few iterations for this problem. Okay, so just to summarize, we have implemented the sparse Fourier transform and the Walsh-Hadamard transform in C++, and it's publicly available on GitHub. So for those who want to play with it and do other things, please do it. More interestingly, it's a source of kind of publicity for me, is that there is a hardware implementation which we did in collaboration with the Berkeley Wireless Research Center, which is the hardware end of Berkeley. And we actually designed a chip, and it actually works. Okay? So this is more than just theory. That's why I wanted to showcase this. One of the information theory highlights is this is I don't know all these details. I don't even know what these circuits guys do, but they do good stuff. Okay? So this is an example. This is where it was published, Journal of Solid State Circuits just recently. It's a 1.89 gigahertz bandwidth, and the goal was to kind of get the heavy hitters in a large spectrum. They want to find out who are the heavy users of the spectrum, but they're very sparse. And it was a good application, and you can see the number of people involved in doing hardware, a lot more than those who do theorems. And for 2 gigahertz bandwidth, the key thing was the acquisition time was of the order of tens of microseconds, which was for this kind of bandwidth is very, very good. And so that's the story. So back to our picture. Remember, I had this picture. This is another instance of you have a peeling-based turbo engine and all these helpers, and they peel away and give you good stuff if they happen. Yeah? Yeah, you will fail. You will know that it won't work. If it is not sparse, if you assumed it was sparse, yeah, you will get junk. You'll get junk. Yeah, because of the, it depends on how you position the tests, right? You will never get any singletons. That means, oh, I have to back off. So you can make things adaptive, and that's definitely, we should think about these things, about going to the next level. This is a non-adaptive scheme, but definitely adaptive. Yeah, you can assume a lot of things and react according to your assumptions. Yeah, these are all grounds for future work, which are very interesting. I agree. Any other questions? Okay, so again, now how much time do I have?
Yeah, so I think 20 minutes is like, and then we have questions.
Okay, so we'll go 20 minutes then. So I'll just skip through most of this because I know it's the same thing over and over. I don't want to belabor the point, but I had a whole bunch of slides prepared. I didn't know how long a 3-hour talk was going to be. So whether I would have the energy or you would have the energy, I didn't know. But I was going to walk through all of these things, but I have about 20 minutes, you said, right? So let me skip through this. While I fast forwarded, you can get a glimpse of what you're missing or not missing. So the key is, again, we do it in sublinear time, compressed sensing in sublinear time. And the structure is, you have your LDPC sparse graph structure, and you have to row tensor it with the right sensing pattern. This is the creative part. You have to get creative here. And when you do that, you can do all these good things. And forget all this stuff. Same thing for phase retrieval, but there are some challenges in phase retrieval because you don't get to see, you can't do peeling, right? At least let me tell you why it's a hard problem. Okay, so x1 and x2 go in here. This is in the singleton case, you would have recovered x1 and subtracted it from this and get x2. What do you have in the phase retrieval case? x1 and x2 are complex objects. It could also be real objects, in which case you don't know the sign, right? The sign is for the reals. So you only get to see the complex measurement, x1. You can't strip x1 magnitude from x1 plus x2 magnitude and hope to recover x2, right? So you can't do that. So there is some stuff involved. And you do it by chaining things and so on. But I'll just showcase the results that you can get order k for the noiseless and order k log cubed for that. And these are some cool simulation results. You can see as I go through the iterations, suddenly you'll see the image of the Berkeley campus because of the channel coding scheme, because it's not gradual, it's sudden. Suddenly at iteration 10 or 11, it'll happen. Yeah.
Does this work only for the nonlinearity being like the absolute value, or can the ideas here be extended to more general nonlinearity?
No, general nonlinearity is open. I don't know. Yeah, you can make it work if you're clever about how you do the singleton test. Yeah.
So there are some assumptions about the nonlinearity.
Yeah, this is for the phase retrieval problem. This is only phase retrieval, nothing else. Phase retrieval is here. And all balls are green. Okay, so, and also a lot of people asked about group testing, but I wanted to honor Jack Wolf, a seminary member of our community. He was a stalwart in working on group testing problems way back when, so let me honor him. And there are some applications to neighbor discovery, and again, you can get sublinear time. At least let me showcase the results. So this is simulation results. So if you have 32 defective items out of 1 trillion, using our scheme, you can do it with 87,000 tests in 0.3 seconds. So it's pretty fast compared to what you could do. So, and this is where number of items is on the x-axis and the average runtime on the right. And again, so I want to stress again, why peeling is hard. This is peeling challenge because you have an OR channel. So you can't just peel. For example, under field arithmetic, 1 plus 1 is 2. Under OR arithmetic, 1 plus 1 is 1, right? So you don't know what happens. And there's a trick for getting around that, but I'll spare you the details. And finally, the sparse mixed linear regression problem. Let me highlight the problem to you. So the motivation is, again, compressive sensing is a powerful tool, But what if you have a mixture of sparse signals? So strict generalization of compressive sensing. So let me at least state the problem. There are applications in neuroscience and experimental design in biology. I'll skip the applications. What's the problem formulation? You have L mixtures of sparse linear regressions, okay? And L is a finite number, say 2, 3, 4. And each of these parameters, each of these linear regressors, beta 1 through beta L, is sparse. And you have total number of non-zero elements in the whole picture is k, which is less than L over n, much less than Ln. Okay, that's the assumption. But you can design query vectors, x1 through xm, which are complex valued, and obtain measurements. And you have no idea, so here's a picture. Here's x, the input, and what you get are, this is your measurement, and one of these three at random will be picked by nature and will be kind of inner producted with this and added to noise, and you get the measurement. This is the setup. So you have no knowledge of which beta L was associated with each measurement. So it's actually jointly or simultaneously, you have to both figure out what the label was and to find the sparse parameters of each. So it's a strict generalization of compressed sensing. Okay? And just to showcase further, so here are my query vectors. And let's say you get those data points. This is in 2D, of course. It's going to be in high dimensions. I can't show it to you. Even rather in 1D. These are my features, and these are my y's. And if I get more, you get that. Do you see a pattern? There, that's the pattern. Okay? For d equals 2 on 1D, you get a pattern like that. And I want to learn the parameters of these equations, but they are sparse because in high dimensions, only a few of these are non-zero. Anyway, so it turns out you can do that, and I won't bother you with the details, but you get basically, I do want to highlight the fact that time complexity is order-wise optimal. You cannot hope to get it in less than theta of k, and you get that. Okay, I'll skip forward through this and go to the last part, okay? Now we're at about 20 minutes away. We're home free. Okay, so the last part is speeding up distributed computing on the cloud. It's work we have been doing in the last couple of years. And this is done with a whole bunch of people. Kangwook Lee, who's joining Madison in the fall. Ramtin, who's at UCSB. Dimitris, who's also at Madison. Orhan, who's still here. Vipul is still here. And Tavor is in the audience right there. He was an undergrad at Berkeley, and now he's at Stanford. So a lot of players. So again, for those who have not heard of this, let me just give you a brief overview. And for those who have, I apologize. So there's a new kind of noise that you have to deal with, not your Gaussian noise or BEC, but this kind of system noise where you have hardware failures, maintenance, network bottlenecks, and so on. And this shows up in the latency variability. In particular, sometimes it completes, sometimes it's still computing. You know how it works on the web, right? It's all because of the cloud. And in particular, if you want to abstract this into a matrix vector multiplication, which is at the heart of many things we do in machine learning, you have to do this matrix vector multiplication efficiently. Otherwise, everything slows down. So the setup is you have a master and many workers. And you want to multiply A by B. Well, you want to parallelize, which is easy to do for this operation. You can give the first 1/3 to worker 1, second 1/3 to worker 2, and the third 1/3 to worker 3. And they each do their thing, and you get the answer back. So that's how you use the workers. Okay, so what's the problem? Well, the problem is, hey, Y1 finished, Y3 finished, and Y2 is taking his own sweet time. So that slows you down. So that's the slow guy, the turtle. Now, it turns out that the straggler, this is called the straggler problem. And if you look at the CDF of the time to collect from k workers, it's been documented from Google Brain and others that the slowest worker can be 6 times slower than the average or the median. Okay. So why do we have stragglers? All the reasons we enumerated. There is data locality, shared resources, network latency. These are things beyond your control. And basically the pervading sentiment is that it's not possible to eliminate all these latencies. You have to live with them and design around them. Okay, so you're stuck with it. This is the noise that we need to deal with. Okay, it's a new kind of noise. Okay, so here's an example, the simplest example of how I use codes for doing this computation. I will divide A into two chunks, A1 prime and A2 prime, and sorry, 3 chunks. A1 prime and A2 prime are now bigger than the A1, A2, and A3 in the previous because I was dividing it 3-way. Now I'm dividing it 2-way, right? But the third one is going to be the sum of A1 prime plus A2 prime. So in this example, here is my Y1 prime, Y2 prime, Y3 prime. Note that I'm computing more because the size of A1 prime is 50% more than A1 in the previous. They were all doing. So I'm going to account for that. I give everybody a fair game. And what happens? Well, as soon as Y1 prime and Y3 prime finish, which will be a little slower than before because they're doing a little extra computing, but it's still much faster than if you had to wait for the Y2 because that was the straggling, that was the bottleneck. So Y2 prime doesn't come, I don't care, because from Y3 prime I can calculate Y2 prime. Okay. So assumptions are you have n workers, k subtasks, and the computing time of each worker is a shifted exponential. This has been shown to be a fairly reasonable model for many of these problems in practice. And note that the average computing time is proportional to 1 over k. So if the subtask size is bigger, then you do less. Okay, theorem. If you did nothing, if you did uncoded, like we saw earlier, the expected time to finish is order log n over n. Well, I could replicate, which was the common theme of the day, before the coding theorists took over, and you don't change the order. It's still log n over n because of a coupon collector effect, which is where the log n is not lost. But if you did an MDS code, which is what our community would have done, you shake the log n factor, which can be significant when n is large. Okay, so here's the theory, which we did in 2015. So for this model, it turns out that the uncoded will give you that point. So this is expected time versus k, the number of subtasks. The replication will give you the purple curve, which is still at log n over n, whereas the coded solution will give you order 1 over n. And this is to show you that in practice, if you run this on Amazon AWS, you get pretty much a similar pattern. Very similar. It mimics the pattern on the left. And you have to optimize the operating point separately for the green and the blue, where green is the replication and sorry, the other way. Green is the coded and yellow is the replication. And you can get significant speedups up to 30%, which can be quite a lot in cloud applications. Okay? So it's a simple way to accelerate cloud computing. So many, many applications. This is a vibrant, rich area since we came up with that work. And the whole ISIT community is engaged on this. I'm sure there'll be lots of posters and papers in ISIT coming up. And basically, the distributed linear regression, distributed nonlinear function computation, reducing communication data shuffling by network coding, all of these are applications. And matrix multiplication, logistic, distributed gradient computing, gradient codes are popular. And then there are also approximations, which I'll talk a little bit about. So the highlight of this is it's a new interface between machine learning systems and information and coding theory. So it's like a API between what they do and what you can bring to the table. You just use it as an interface and things will just go faster. Okay? So they also like that because they don't want to know what's inside. Just like you don't want to tell them what's inside, they don't want to know what's inside. And codes can be used. And this is to show that matrix multiplication, linear regression, and matrix completion, some examples, your speedups can be on Amazon EC2, on real data, this is actual data. You get speedups of 33, 25, and 38%. Okay? This is in practice. And as I said, this is a laundry list of all the coded computation work that's gone on in the community and still growing. There's many more things to be done. So what I want to talk about is, instead, I want to switch gears and talk about the future, what we think is the future, and which has to do with going serverless. So it's a strange word. What do you mean serverless? It's called scalable computing for serverless platform. So a decade ago, cloud servers abstracted away physical servers, right? So you used to have physical servers. And they said, oh, it's in the cloud. Don't worry, it's a virtual server. In the future, the vision is that serverless computing will abstract away cloud servers. So you don't even need to have cloud servers. It's some object. OK, so now this is where I kind of interact with the Berkeley folks in the RICE lab. I don't know what RICE stands for, but one of those acronyms. But it's a very influential lab. And they view this serverless platform as a function as a service, FaaS. Run my function somewhere, I don't care where. I'll tell you some of the advantages. So here's the cloud storage unit. Here's your function f, and there's the data. And the serverless workers are lined up on the right, and each of them is entrusted with computing the function or part of the function. But they have to interact with the main cloud storage for getting the data, and because they themselves have very little memory attached to them, but they have CPU, they have processing power, but there's a lot of I/O. They have to go between the main storage and what they have. And they then have to write the results, and you can poll them and get the results. So this is the serverless platform, and this is getting more and more popular. AWS, Google, IBM, Microsoft are all kind of embracing this architecture. Why serverless, right? You may ask, what does it do good for me? Why can't I stick to the master server client-based that we saw for EC2? Well, first and most important reason is that it makes it very simple for the user. Right now, if you want to use the cloud, you need to be an expert. You have to provision this, do that, get all kinds of stuff, and then if you're lucky, it may work for you. The goal is to make it like anyone can come and go. Okay? So cluster management issues are hidden from the user. This is the number one reason. And it's got tremendous scale. That's also good for us. We want scale. We want asymptotics. Here's asymptotic. So you have 16,000 machines for 10 seconds. And in 10 seconds, rather. In 10 seconds, you can invoke 16,000 machines. And you can think of the cloud storage as an infinite RAM. So you don't have to worry about that. But you do have to worry about communication cost. OK. Even better for us, right? You want schemes that need to worry about communication cost. And finally, you pay as you go along. You pay as you use. So these are reduced costs. Based on how many times you use, you pay for it. And there is significant interest from the cloud computing community for this architecture. So if nothing else, we should be aware of that. And whatever our future lies should intersect with that, because that's where the world is going. OK. This has been articulated really well in a recent Berkeley article, Cloud Programming Simplified, a Berkeley View on Serverless Computing. This is by the systems folks. Okay. So what are the characteristics? So I'd rather dwell time on explaining this rather than going into results, because this is important. So you have a massive scale of low-quality workers. These AWS Lambda is the platform for Amazon. So these Lambdas are these tiny workers that come and go. Okay? So they do not communicate. They do not communicate with each other. So they read and write only through single data storage, and they are short-lived, they are ephemeral. So, and in this kind of wild, wild west type of environment, you are bound to have stragglers, and you do find stragglers. And that's where our community can come in to the rescue. And you have false also. So here's a kind of plot of, on the left is a single run snapshot, and on the right is the average runtime over 10 trials. And the key point is, if you have 16,000 workers, what are the odds that they all come together? Not going to happen. So you're going to have a significant number of stragglers. But I want to caution about where the community is headed in terms of what is the problem we are trying to solve. We are solving a time problem. Okay? We don't care if it is MDS code or that code or this code. It's all about time. Whoever has the shortest time under these conditions wins. So you have the input. Here's my black box, which is the encoder with these processors and the decoding. So in general, matrix multiplication is a black box, and MDS is beneficial, but it targets only the computational part of the whole picture. In particular, end-to-end latency is what we should target. There's a time for encoding. There's a time to distribute it among the processors. There's a time for doing the computation. This is where MDS shines, because you need the fewest number and they come, whoever straggles is left out. And then you have a time for decoding. It's really the sum of all these that you should measure your time clock. That's who wins the race. So when you do that, at least for the serverless architectures, we find that product codes are a much better trade-off than polynomial codes and Reed-Solomon codes and all these things, mostly because of the encoding, decoding aspects. And here's an overview of, I'm not going to dwell on product codes, but they're also closely linked to so-called generalized LDPC codes studied in the literature. For an example of matrix-matrix multiplication, let's say that, so product codes came first, Elias in 54 and Justison in 07, and we had some work in 15. And generalized LDPC codes kind of generalized this and cast everything in a much more general framework. But here's the key idea. If you want to multiply A by B and you have A1, A2 and B1, B2, you just expand A1, A2 by one extra row and one extra column. And when you multiply them, you have this particular matrix. Now, what are the characteristics? It's near MDS. It's not MDS. You have very low encoding and decoding cost. It's parallelizable. And you can generalize it to n dimensions or d dimensions. It's some work we have done. Now, here's a 2D version. So these are the parity computations, if you will. And in 3D, you will have a cube where all the corners are taken by parity. And more generally, in d dimensions, you'll have your own structure. So the key point, to come back to the theme of what we've been studying all day, is product codes are decoded using peeling, our favorite toy. And they fit very well. So here's an example of the red are the stragglers and the greens are the good ones. Peeling decoding is very simple and parallelizable because I'll first look for all the rows or columns that have a single bad thing in them, singletons, and get rid of them. That results in new columns, and then you're done. Okay, so how many do I need and what's the computation? So Tavor and I looked at this last year for a d-dimensional product-coded matrix scheme, where this is NKD, this is the distance of the code. That means this can correct R stragglers. You have component codes. This many component codes, so every row and every column is equipped with this structure. You can show that the output will be decodable with high probability after this many nodes have completed. It is almost MDS, if not for this eta, right? If the eta was 1, then this would be n minus k, which is k, which is the best you can do. But because of the eta, you get a 22% hit in the case where D is 3 and R is 1, meaning it's a 3-dimensional product code with a single component on each dimension, will give you about a 23% hit in terms of the MDS property. But because of the encoding and decoding speeds, it's an overall winner. And more generally, the key thing is that these two worlds of product codes and LDPC codes or this density evolution, for the experts, they know that they are connected. But I just wanted to kind of make a comment that these two worlds can actually come together. They're actually the same world. So you can actually analyze these using the density evolution equations I showed earlier. And so that may be an interesting intellectual bridge, which was known. I don't want to claim that this is the first time it happens, but it was not popularly known. At least I didn't know it when I started working on this problem. Okay, so you can tolerate n minus k over 1.22 stragglers. Okay, so now it's just showcasing some of the applications we have done. Again, we are using the lambda structure, which is the serverless structure. And it's about 400,000 examples with 400 workers. And this is a kernel ridge regression learning problem. And I'm not going to go through the details, but to point out that the bulk of this is to solve for this matrix vector equation, where you have to keep solving for this iteratively. So k plus lambda I has to be multiplied by k, and lambda I are known, but xk keeps changing in every iteration according to the conjugate gradient method. And shown here is the iteration number. In red are the speculative execution. This is what people do today. What do? They wait to see if something goes bad, and if nothing goes bad, they say, good. If something goes bad, they say, let's run up some more machines because this stuff is not coming in. And they have some heuristics for when they do speculative. At what time should I speculate to re-execute? Okay, that's the state of the art today. But with coded computation, not only do you cut down the time, but more importantly, you cut down the variance. See, the red guy is wild, up and down, but the blue guy is pretty steady. So that's much more important for them. And reduced variation. And if you look at the actual time savings, in blue is the coded scheme, and in red is the speculative execution scheme. This is the iteration number and total time. You will save about, I think, 45%. Significant. Okay. Same thing with another application which has to do with PageRank, and where we use the power iteration to keep computing the largest singular value, largest eigenvalue. So they are of this form, right? You iteratively. So why are you winning? Because you have to constantly do this iteration, and in each iteration you have stragglers. So it's a cumulative effect. So you will shine if you have to do lots of iterations. Then for sure the competition is going to straggle heavily. So that's where you can showcase the gains. So you can see here that there's about 50% gains for this application. In terms of total amount of time taken, you know how long it takes to run on the cloud, you're taking 1 hour less, which is a significant amount of time. And finally, to get to the last part of my story, I want to talk about something which has been happening more recently, which is that exact computations, which is typically where codes shine, is kind of not needed. It's overkill for many applications, especially if the input data is redundant. And randomized sketching is an important way to reduce computational complexity. And this is work done by my colleague Mike Mahoney and co-authors, and there are many others. And what's the idea? So typically you'll have to compute something like AA transpose. Okay, this keeps showing up in the iterations. So I don't want to do AA transpose because it's too big. A is too big. And not only that, there's no real value in doing the full AA transpose. Might as well do an approximate version of AA transpose. And that's what you do by multiplying A by a sketch matrix S on the right. So that's what we do here. A is D by N. N is huge compared to D. And S is N by M. So N is the sketch dimension. And M is the how much you reduce N by. So you can see that when I multiply A by S, I get A twiddle, which is D by M. And the hope is that you can make M much, much, much smaller than N. Okay. And S is a random matrix such that S transport is close to identity. When you do that, A tilde transpose will be close to AA transpose. Okay, that's the big picture. So in particular, for large-scale optimization, convex optimization problems, the real challenges, as I said, in the serverless systems to review are slow communication, ephemeral workers, persistent stragglers. So reducing the number of iterations is really important because that's how many times you have to go back and forth to memory. So second-order methods, which have been shunned by the community because they're too expensive in the classical setting, suddenly become very attractive here because they're a natural fit for serverless systems. So this is something that we have been pushing and we feel excited about. So because second-order methods, like Newton's method, have much fewer number of iterations. For convex problems, they converge in quadratic convergence. And they also, the other point is, you can exploit the tremendous compute power we have at our fingertips because you have all these lambda machines lying around, and they're all powerful enough. Or if you are not powerful, invoke some more. There's no problem. And the cost is not that much because you pay as you go along. So from an economic standpoint, this is very attractive. So we are proposing something called oversketched Newton, which is tailored to serverless systems. So what are the key observations is that the gradient can be written as a few large matrix vector operations, and the Hessian, which is the second derivative matrix form, can be written as a large matrix computation. That's all these things are. So many problems in which they apply, from logistic regression, softmax, SVMs, linear programs, and so on. So all of these can benefit from this. So as an example, if you look at logistic regression with a regularizer, so again, X is the matrix containing the training examples, and Y is the vector containing training labels. The gradient is given by this expression, believe me, it's not that hard. But the key thing to observe is that it essentially contains two matrix and vector operations. First you have to compute alpha, which is X transpose W, and then alpha goes into the definition of beta, and then X times beta is computed. So X beta and X transpose W have to be kept on being done, many rounds. Hessian, if you take the second derivative, it turns out you get that expression. And again, the key thing to note is that it requires computation of A transpose, okay, multiple times, where A is X times square root of lambda. Okay, these are details, but the key high-level point is this is nothing but a few matrix vector. This is nothing but matrix. So what's the idea? The idea is twofold. The gradients turn out to be important because when you're doing Newton method, if you don't compute the exact gradient, you can be off in your performance. So let's invest in computing the gradients exactly. We know how to do that. We just went through how to do matrix vector using coded computation. Now, what about the Hessian? There, you don't need to do exact. So let's just do it approximately. But what if there are stragglers? You do something called oversketch. So in the terminology of information theory, oversketch is just joint source channel coding. Okay? Because sketching is source coding, compressing, and oversketching is leaving some room for channel errors, but doing the same object. So you do it all at once. This is called oversketching. So that's what we show here. So here is the gradient computation, which is computed in an exact way using codes, like we discussed earlier. And the model update consists of this equation where H hat inverse can be done locally if D is small enough. So what do? You sketch. This is how much you would have sketched if there had been no stragglers. You just do a few more, and that should cover it. So we can also show that you can prove convergence guarantees of this oversketched Newton for both strongly and weakly convex cases. And here are some kind of comparisons. So giant is the current state of the art in second order methods, which is globally improved approximate Newton. This was done in NeurIPS 2018. And it's kind of a setup where you have 0.3 million examples and 3,000 features. And we are doing this on the AWS Lambda. And shown here are various plots of the giant algorithm, which was done by Shushan Wang and co-authors. And basically on the x-axis is the time, and the y-axis is training error. So you want the training error to be small. With full gradient, you get this, and then with gradient coding and ignoring stragglers, which is what is typically done, you get the last one. Now, the exact Newton's method, that you would have 3,600 workers needed. Of course, workers are cheap, so you invoke them. You get an improvement in terms of the number of seconds for getting a particular accuracy, but this assumes the exact Hessian. Now, if you relax that and go for the sketched Hessian, the oversketch, you can improve on all of those. So you can see here, this is the oversketched Hessian, and you get 50% savings over the exact Hessian for the same error probability, error threshold that you want. for logistic regression on synthetic data. So this is kind of a promising scheme. And you only use 600 workers because you're sketching. You don't need the full 3600. So here are some examples showing going from left to right or top to bottom, the effect of doing codes. This is using no codes, using codes only for gradient, using sketching only for, over-sketching only for Hessian, and then doing both. You can see that there is a hierarchy of techniques, and doing codes for both, I'm going to call over-sketching as a code. You actually win on this, at least on this particular application. And finally, this is kind of an interesting plot because it was not thought that this giant scheme that we talked about runs on a server-based so-called Amazon EC2 scheme, which is a standard scheme. And for the most part, the Lambda systems, the serverless systems, were not able to beat those schemes before. This at all. This is just the communication cost. All this stuff is too much. So, but surprisingly, you win quite a bit, at least for this application. I don't know if this is universal, but you see the giant scheme on training error versus time goes down like this, but the oversketched Newton actually beats it. And this is kind of interesting because there are not that many instances of serverless systems beating server-based systems. And so I believe that this is kind of indicates there's a good direction for the future. And also because this is rich with coding type ideas that can be brought in. Okay, so I'm going to conclude a marathon session after many breaks and so on. But what we have seen is we've covered a lot of ground. You guys are still awake, so that's a good sign. So I showed you first, we dwelt on duality, how you can exchange the encoder for one for the decoder for the other. We went through some exercises in doing information theory, toy problems and proofs and so on. Then we went to encryption, where I showed you this swapping the order of compression and encryption, which is highly non-intuitive, is actually possible, and without any performance loss as well, in theory. Then we looked at sampling, where we showed that for sampling below the Nyquist rate, you can explore interesting connections between sampling theory and coding theory that were not known before. And you can you can actually sample at sub-Nyquist rate at a cost proportional to the occupancy of the bandwidth. Then we went to learning, where the key was the core was this powerful sparse graph code engine with many sparse settings with sublinear time complexity. Sublinear time complexity is a pervading theme through all these projects, which is, again, I want to emphasize, most people just care for performance. If your capacity achieving, are you there within factor of 2? Oh, I'm 1.2. I'm not sure that that's not good, that's fine. But an ignored aspect of it is the complexity. And if you take the complexity as your perspective and say you must be sublinear time and find what's the best you can do, you will find that you're, surprisingly or not, you will find that you're not that far from what you would have done if you had ignored it. So that means it's a win-win. So, and finally, I showed you our recent work on distributed computing, where you can straddler proof these codes, and more generally, we can go to second-order methods for serverless systems. Okay, so with that, let's again conclude with paying tribute to Shannon, because this is the information theory school. All his things are being represented in the tutorial I gave, and of course, his legacy will last many more centuries. With that, I will quit and take your questions. Let me get some water first. My throat is dry.
Yeah, so, and I have no peripheral vision, so just stand somewhere. So we'll wait for some.
Yeah.
In the distributed computing, in the
very beginning example matrix.
Which example?
In the very beginning example,
Yeah.
matrix by vector
Yeah.
multiplication. Are you considering in the real field?
Yeah, everything is in real.
So MDS codes are
Yeah.
basically in finite fields, and the arithmetics are done in finite fields. How
Yes.
do you?
Yeah.
deal-
No. MDS, I introduced that in, for those schemes, we were just doing a single parity or something. The MDS was in the sense of, if you have a single parity, then real and new are kind of the same thing. Because you have to add or subtract, right?
Okay.
So, but you make a good point. I'm not a fan of using MDS codes for precisely that reason, because you need to have numerical stability. And since you're working in the reals, you often have to quantize it and then go back to the reals. Yeah, you can do it. A, it's computationally intensive, and B, it's not very stable.
Yeah.
Yeah, so you're
That was
absolutely
my
right.
point.
No, that's
So-
the product codes don't have that.
So basically, you are using the binary codes. In the real. The LDBC codes are just
Everything
zeros
is
and-
on reals. Yeah, even all the stuff that I've talked about is on reals, right? The DFT is on reals. Everything is on reals. I don't care about which field. In fact, reals are good for me because I'm only doing peeling, right?
Yeah.
That's why peeling is very attractive. Yeah.
Thank you.
Sorry, I thought I saw one more, but I lost track. Nobody else?
I think people are hungry.
Hungry to present their posters.
Hungry to present
Right.
their posters.
Yeah, okay. So no more questions then. First, let's thank Kannan again for a wonderful presentation.